this webinar is also very appropriate. The journey of computer from 1940 to till date has passed through several generations of evolution from vacuum tubes, transistors and diodes, integrated circuits, and microprocessors. In those generations, efforts was made to incorporate more and more circuits in a single CPU. But now, in fifth generation, it is turning to massive number of CPU for added performances. We'll be able to know more about future generation computing from today's and tomorrow's deliberation from the experts and enrich ourselves. I thank you very much for your participation. Let us make this event a grand success. Thank you very much for giving me an opportunity to share my views. Thank you.
Thank you, sir, for your kind words. I would like to welcome Professor Saikat Maitra, Vice Chancellor MAKAUT, to please give the keynote address. Please, sir.
Okay. Thank you, Chatterjee, for inviting me to deliver my views on today's topic. And this is very nice to be among you. Dr. Krishnendu Chakrabarty, Dr. Rituparno Sen, and all the faculties. I have been closely connected with them since a long time. And this is a rare opportunity for me to be among you again. And it's great that you are organizing these types of webinar on future generation computing and application. In this present context, it's apt and useful in the sense that this time is a different time. And a long time before, when Charles Dickens wrote these lines that it was the best of time, it was the worst of time, in the context of French Revolution. In this context of technological revolution, and in this context of this worldwide pandemic disruption, these lines are again becoming relevant and contextual. What we are observing in the last 1 decade, there has been a phenomenal change in each and every aspect of our lives. This year, this pandemic scenario perhaps accelerated some of our practices, but some of these things were inevitable. Professor Chakrabarty briefly narrated the evolution of computers. One of the interesting aspects of these transistors, when Moore of IBM, he first proposed his hypothesis as a famous Moore's law, that within 10 years, the numbers of transistors which will be housed within a definite space of areas, that will be doubled. In 1965, when he proposed that, he did not imagine, but by 1975, it would have been revisited and corrected with the time span of 2 years, not 10 years. And this is the reality. This is the reality of exponential development and growth in the field of microelectronics, computational science, and that has become more acute in this century. Perhaps this Moore's law needs to be revisited again for describing the time span which will be required for doubling or tripling or quadrupling this entire phenomena. You see, when this industry first started in the form of Industry 1.0, The basic features were in the 17th century or 18th century, perhaps 18th century. This was predominated by the emergence of mechanical engineering. In Industry 2.0, after almost 100 years after this Industry 1.0, when it started, the major feature of is this emergence of electrical engineering. This assembly line, mass production, that became the feature. And for Industry 1.0, it was the mechanization of all things. But after Second World War, when Industry 3.0 started, the domination of electronics and microelectronics, that became profound and evident. In between, there were certain intermediate stages of industrial revolution in the form of Industry 3.5 in 80s and 90s of previous century, in the form of shifting all these manufacturing units from developed countries to the less developed or underdeveloped or developing countries because of the pressure from environment, pressure from society, pressure from all the resources like water, and to get access of mass market and to take leverage of cheaper production. But when Industry 4.0 started in this century, in the first decade, the major facet of it was automation, analytics, remote work process, artificial intelligence, robotics, and cloud technology. That became major feature of this industrial changes or transformation. Digital transformation that started to penetrate and affect all aspects of manufacturing sector, service sectors, and other spheres of our life. Even if say 10-15 years before, we never imagined smartphone will be a major part of our entire life, and many things can be done with this, with the use of smartphone, be it booking of cab, booking of hotel, booking of air tickets, or payment of this to different clients and customers, avoiding cash handling. So this is the future. And by 2024, the cycle will be completed. It is being said that by 2024, this Industry 4.0 will reach its peak level. What we are observing in the last few years, there is a mismatch between the demand and supply of our output in terms of these products or the knowledge generated by most of this academic institute from different engineering and professional programs. The reason behind it is we were a little bit hesitant. We are lagging somewhat in embracing all the digital culture. And we could not make it an integral part of our entire system. So this is the one of the this reflection for worst of time part. But this COVID-19 on this pandemic scenario has accelerated this process, has forced all of us to embrace this digital technology to the best possible extent for our survival and for our growth. We have no other option left. And that is evident from different facts, figures, and statistics. If we look at our industrial sectors, most of these things be it heavy engineering, be it light engineering, be it small-scale sectors, you will see robotics and remote controlling process is controlling the manufacturing process for all these industries, all these manufacturing things, for better control of products, for prevention of wastages, for handling this hazardous process in a better way, for taking care of the environment, for controlling the entire supply chain process, for controlling this maintenance of inventory, warehouse, all these things. And because of these recent changes in geopolitical equation, one of the opportunity for India is now for many manufacturing sectors, destination India has become one of the viable options. You have read probably in newspapers and magazines and watched in this internet or televisions, many of these world giant in manufacturing, they are shifting their manufacturing base to India. We had this problem because of the fact that when this IT revolution started in India, we neglected our manufacturing sectors and focused on IT sectors or service sectors to the maximum extent. And as a result of which our growth and development in manufacturing sectors, that is not that much appreciable compared to our neighboring countries. But the chances has now arrived at our doorstep. And this is the time to engage ourselves in meaningful activities pertaining to all these things. You see, this survey by different professional organizations like NASCOM or like this Times and all other the market survey agencies. For India, the prediction is the maximum numbers of jobs will be created in machine learning and artificial intelligence in near future. The importance of artificial intelligence is such that the government of India has published its AI policy for all sectors. And that policy was published by NITI Aayog a couple of years before. It covers almost all sectors: agriculture, healthcare, social sectors, all sectors are there being covered. The next, second stage of demand will be for data science, then cyber security and all these things. This is quite this important in this aspect. You see, in our country, if we look at our resources, our potentials, till now, we could not leverage all these natural benefits. We are blessed with vast agricultural lands. We are blessed with the right types of climates. We are blessed with this biodiversity and all these things. Now we have to look, or we have to take advantage of all these things, all these subjects, particularly this latest state of knowledge in taking benefits from all these sectors. For agricultural sectors, precision agriculture or smart farming is the call of the time. And what are the features of precision agriculture, smart farming? It is based on this cloud-based technology, IoT devices, engagement of robots, or more yields, more crop yields per hectares of land or per acres of land. Digital health in healthcare sectors. In India, we do not have the facility to provide healthcare facility to persons who are staying at the remote corners of this country, belonging to the disadvantaged group. Now, people are understanding the importance of digital health, engagement of IoT, engagement of robotics, telesurgeries, telemedicine. All these are the features of this digital health. And this is true for each and every sector, and education is also no exception. Coursera, when started in 2012 as a startup, by two professors of Stanford, Professor Duflo and Professor Andrew Ng, with some seed capital from Stanford. They never imagined within a span of 2-3 years, it will bring a revolution to online education system. MIT, of course, started it earlier. And the importance is such that for online education systems, Government of India started some, IIT started there, NPTEL, spoken tutors. Now everything has been merged with SIAM and all these things. Access to the quality education, persons staying at tier 2, tier 3 cities and villages is possible only through this digital path and digital routes. People are talking about digital divide. What I see is a digital opportunity. We never imagined that when we were student, without visiting MIT, we would be able to attend the classes of MIT professors or Harvard professors. Now it's not a problem at all. If you have smartphone, you can jump into the classes of all these professors. You can get quality learning and certifications from all these universities through different platforms or from the university itself. And that is much affordable compared to our traditional education systems. Probably you are aware that large numbers of degrees being offered at online platforms in IT, computer science, management, and all in other disciplines by different universities and by different online platforms. And the advantage is if you get enrolled to all these programs, all these certificates are being is connected to your LinkedIn profile. Google's are taking note of all these things. Amazon is taking a note of what you are doing through their analytics, and your employability is also enhancing. So this is the changed world. We have to integrate our all activities with this digital world to the best possible extent. So in this sense, this machine learning, understanding of machine learning, it is not the domain of only computer science and IT. This machine learning and understanding of artificial intelligence, it should be for each and every branches of engineering and professional programs. Same is for data science. Same is for data security. Everything will happen in digital platforms. Everything is happening in digital routes. So this, how to safeguard this data, how to protect this data. So data security and all these things are become more and more important. So we need to understand these subjects from different disciplines, because the fact is this, machine learning is nothing but it's a tool. And if the conceived problem, that problem can be solved by all these tools. If we apply different perspectives and different approaches. So now this is the time to understand and integrate all these approaches to our system, our research systems, our education systems, our these application systems everywhere. It is being said that the famous phrase is break the silo. Now, this is the time for theory of everything or understanding of different subjects or importance of multidisciplinary or evolutions of 360-degree approaches. So all these things, it's related to the fact that we need to have effective integration and collaboration with these tools and techniques for taking care of all the existing problems in our society for its gainful solution. And therefore, these subjects, this further generation computing, machine learning, I do not know whether cyber security, data security will be there or not, but this needs to be incorporated. Data science will be there or not, but this needs to be incorporated. Data analytics, otherwise there is not, but this needs to be incorporated. And quantum computing, this is going to bring some further revolution in our computational things, because this is the time for handling big data. Whatever we are doing as a pocket research, handling with small data in today's time, that has been proven that it is of no use until and unless if we are not in a position to handle voluminous, diverse, heterogeneous data from different sources and processing this data for getting meaningful solution, be it genomics, be it environmental aspects, be it agricultural aspects, for all sectors. With climate change, everywhere we need to handle with this big data because of this heterogeneity and diversity, and which is more prominent, more acute in a country like us. That's why when I was asked these questions, what is your opinion of this policy, education policy, or all these policies? My one-line answer is, each and every policy will be successful if it take into confidence and consideration of all the stakeholders in a diverse and democratic country like India. Similarly, if we do not have the capacity of handling big data in a country like India, whatever the outcome of all our activities, that is not going to give dividend. So therefore, you see, these tools and techniques, this needs to be understood by all the stakeholders of our education, research, and learning community. Primary understanding of artificial intelligence, machine learning. Machine learning is artificial intelligence, a bigger domain. Machine learning is a part of it. Understanding this, basic understanding of programming, understanding of Python, understanding of data science, understanding of analytics, different sorts of analytics. So these are becoming, this essential component of our education system. Now, my message to all these participants over here is take active interest. One of the problem of engaging ourselves in all these digital practices, we are missing our physical warmth and proximity. It is difficult to keep your attention for a long time sitting behind the computer screen and listening from other end continuously. It's difficult. That's why it is being said, the ideal way of doing this learning practices in digital platform is minimum intervention, maximum engagement. It has been proved that all lectures, if it is more than 8 minutes of duration, all these lectures with digital lectures, the attention span drops drastically. So that is a standard practice is not to give lectures for more than 8 to 10 minutes and give more learning resources to the participants, to the learning communities, and engage them in peer-to-peer activities, in a collaborative activities. One of the important things I'd like to share with you, long time before, when that was the time of old civilization like Greece, like India, China, and all other countries. If you look at Wikipedia, there is a photograph of Plato's Academy. That fresco is at Pompeii. Pompeii is at Italy. Probably you have heard the name of the books or have read the books, Last Days of Pompeii, the famous city which was destroyed by the volcanic eruption from Vesuvius. A fresco is there. And what is the significance of the fresco? Because it is being presented at different occasions. I do not know whether I am getting diverted or making you bored with all these things, but this is the only one opportunity for meeting you. So maybe many things I am telling, but everything has this heart and this orientation. You see, this the significance of these pictures is, if you look at it, you will see few persons are in a standing mode, and in the center place, two persons are there being seated, and it appears that talking to each other. What is the significance of it? This pictures was used by first University of Illinois to make this fact. Why Illinois is important? Because Illinois is the first university to introduce digital education, online education through a computer system which is known as Plato in 1959. They are the pioneer. And if you go to the website of Illinois, you will see that they are the top university of the world to have a large numbers of courses in digital pedagogy and e-learning and online learnings. So they use this picture to people understood the importance of this pedagogy in the form of dialogues, or which is called dialogic pedagogy. Two persons are talking. They are basically debating. They were basically debating. The one of the person was Socrates, and another was his teacher Plato. That time, this concept was all of this learning or knowledge that will be evolved out of dialogues, out of discussions and out of debate. Same system was there at India. And in 1913, they also mentioned, I have taken this almost all these programs from Illinois University. I know all these things. They mention another gentleman. You will be surprised to know he is none other than Rabindranath Tagore. It's a matter of proud for me, at least, when I observed that as Illinois professors, they were showing the photographs of Tagore before starting their these classes. And why this is so? Because they were telling that in 1913, Tagore was there at Shantiniketan at Illinois, because his son was there to take this education in agricultural engineering. And that in that year, Nobel Prize was declared. Tagore was the recipient of Nobel Prize in 1939. At that time, he was at Illinois. He engaged himself in active discussion of these learning systems, why it is not, generating the results of this. That time, the modern or so-called modern education system is not generating results. And he had his conviction that this system of education, which we are following, this method of education which we are following, is not going to give these desired results. This classroom-bound education. So that's why this conception of Shantiniketan he conceived. And this digital form of all these things, this digital education, all these things, it has one of the biggest advantage of engaging a large number of communities. If you have discussion forum and front, anyone can put their comments there. And on these comments, anyone can put further comments. If you tweet, another person can retweet. If you post something at Facebook, another person also can post something else. And out of that exercises, be it blog, be it social media, and everywhere, you will see there is an evolution of emergence of knowledge and idea. This is my observation. In future, it is going to happen more and more with the embracement of all these things, digital tools, techniques, and understanding of these computational tools and techniques. That's why, irrespective of each and every subject, we need to understand these different aspects, at least to a certain level. Of course, in computer science and other areas, we will be there for taking the subject further by doing meaningful researches and all these things. But for the onus is on us also to have this understanding so that we can conceive the problem. And if we can conceive the problem, 95% of this is over, 5% is required. This is Einstein's statement. Design the problem first, and it will take 95% of your time, and 5% of time will be required for solving it. And that requires a multi-dimensional approach. And for that, one of the strongest and potential tool is all these computational tools and techniques. So thorough understanding of our own subject, peripheral understanding of these computational tools and techniques. This is going to give us dividend in new India, in new times. And my belief is that today's generation, their IQ level is higher, intelligence level is higher, because artificial intelligence is evolving, biological intelligence is also evolving. So we have to engage our young learners in this meaningful activity and try to kindly give them all these resources, learning resources available for these discussions and all this, associated with this topic, so that this can be sustainable and effective. And after doing all these things, maybe you can have a calendar for organizing these again and again, so that it become there's a sustainable knowledge generation activity. With this, I wish you all the best. I wish a grand success of this program. I have taken enough time, and if I made you disinterested of all this in the digital platform at the outset, let me apologize for that. Thank you.
Thank you, sir, for your inspiring and interesting words. This concludes the inaugural session. We once again thank Professor Saikat Maitra, Honourable Vice Chancellor MAKAUT, and Professor Krishnendu Chakrabarty, Principal, Government College of Engineering and Ceramic Technology. We will now begin session 1 of our webinar on Perceptron Network to Deep Networks, a walkthrough by Professor Amlan Chakrabarty. Professor Amlan Chakrabarty is a full professor in A.K. Choudhury School of Information Technology at the University of Calcutta. He was former Dean of University of Calcutta. He is an MTech from University of Calcutta and did his doctoral research at Indian Statistical Institute, Kolkata. He was a doctoral fellow at the School of Engineering, Princeton University, USA during 2011 and 2012. He is the recipient of prestigious DST Boycast Fellowship Award in Engineering Science, Indian National Science Academy Fellowship, JSP Invitation Research Award, Erasmus Mundus Leaders Award, and Hamid Visiting Professor from University of Cambridge, and Shiksharatna Award by Department of Higher Education, Government of West Bengal, 2018. His areas of research interests are quantum computing, reconfigurable computing, embedded system design, VLSI design, computer vision, and machine learning. I would like to invite Professor Amlan Chakrabarty to begin his talk. Sir, please.
Yeah, thank you, Professor Kingshuk, and thanks to Professor Maitra for his great elaboration on the present perspective of digital era and how academics and how research will go hand in hand together. I also have Krishnendu Chakrabarty. Professor Chakrabarty was my first principal of my college. Okay, and thanks, Professor Chakrabarty, for inviting me once again. So thanks to the organizers of the Ceramic College of Engineering and Technology for inviting me, and I will now start my presentation for you. So the title of my talk is a walkthrough from Perceptron networks to deep networks. And as we all know that the deep network is something which is playing a great role in the present scenario of the applications of machine learning. But to know the deep network, so I think I'm audible and my screen is fine.
Yes, sir, you're audible, and the screen is visible.
Okay. So this lecture will try to enlighten the way we moved forward from the fundamental perceptron network, or commonly known as the artificial neural network, to the deep network, and also I will discuss the key techniques that are employed in the deep network, and some of the ways we can apply the deep networks in many of the challenging problem areas. So when we look into the modern era of applications, right, we see machine learning is everywhere, right? That means might not be the person who is using the applications they know that there is a machine learning which is working to support the application, but these applications are very interesting, and these applications are serving the purpose of the society in many ways, right? For example, obviously machine learning, the way we do the computerized games has a great impact in the progress of machine learning. A lot of machine learning algorithms were being inspired for developing very intelligent games, and that's obviously one of the areas. But also there are a lot of recommendation systems which are in the retails, which are in the online entertainment systems. news systems, news channels, online news channels. So these recommendation systems also are very well done by the help of machine learning. The great societal impact, in the terms of drug discovery, in the terms of bioinformatics, how to analyze the molecules, how to extract the effect of a drug on our biological system. These are very complex models, and machine learning plays a great role there. Obviously, the pattern recognition is one of the key pillars of on which the machine learning algorithms are developed and are well applied. And character recognition is one of the key issues, the character to text conversion, text to speech conversion, speech to text conversion, developing different types of interfaces for human computer interaction based on character recognition is one of the key areas. Obviously, we cannot miss out the financial segment. A lot of financial plans, the prices of the stocks, the financial growth, the predictions are based on analytic models, business analytics models or financial analytics models, which are predominantly worked upon by the machine learning tools and techniques. And similarly, the latest introduction of support systems in our digital platform, which are called bots, right? And these bots are nothing but digital assistants for different type of services. Their services are offered to the digital platform, and we know that the banks, the retailers, the big companies where we want to buy the products or we want to inquire about the products. And nowadays, many of the universities and many of the training institutions have also started the apt use of this particular technique or technology to support the users or support the students. In nothing less, also the domain of automation, like self-aware systems. A good example of this is assistant driving, where we have autonomous car and autonomous vehicle, and there can be multi-purpose autonomous systems, which all falls under the big influence of machine learning. So obviously, the computer vision is one of the key areas, and computer vision with overlapping of pattern recognition is a key area of our machine learning application, and biometrics, face detection, fingerprint detection. So all comes under the purview of this particular domain of machine learning. And last but not the least, obviously cancer diagnosis. In terms of analysis, the images, the radiological images of the patients, or doing the analysis, the microscopic images of the cells or the tissues. Those leads to a lot of diagnosis, which can be done in an automated way to the techniques of computer vision and which are boosted upon the machine learning tool. So I have what I have told is only maybe a very very small fraction of the things what we are using in the various operations of our life, but there are many more. That means there are domains in security where machine learning is playing a great role. There are predictions in terms of weather, in terms of climate, in terms of land patterns. So this is really a big basket, and the basket is getting bigger and bigger as we progress and as we see the evolutions of the machine learning strategies in each day of our scientific progress. So to touch the basics, what is actually machine learning approach in a very fundamental way? So normally the hard-coded approach is some test on an algorithm-based system. So which means that I want to understand the problem, and I know that this problem can be matched with other algorithm. This problem can be solved with algorithm A or algorithm B or algorithm C, and then we try to define the algorithm which can solve the problem, and try to code the algorithm and put into the system. So so this is called a hard-coded approach because the system cannot change its logic, okay, as the algorithm is very static. So whatever data comes, whatever varieties of data comes, the system works in the same logic, right? And that's what's called the classical computing engine or classical computing systems. Now this system fails in many of the modern needs because due to the variety of the input what we give. Suppose I plan to do a retail, an engine of a retail engine which will suggest that what are the things to buy. So now if my algorithm is based on some understanding that a particular person buys X and then buys Y, but this particular person has a huge variability, right, in terms of gender, in terms of age, in terms of its economic background, in terms of its social need, in terms of its academic background. So you see that there is a large amount of variability which can happen, and when we have this amount of variability in our data, the static way of algorithm development or the classical way of developing algorithm fails to many of the to give a very useful result. Right, and that's why we adopt the path of machine learning. And what machine learning does? Machine learning doesn't develop the algorithm, in the form of the perception which the designer abstracts. Rather, what it does, it will try to generate the perception from the data itself. Right, it will try to do a discovery on the data and try to find that what emerged out of this data. Right, and from that it tries to generate an abstraction, a knowledge representation from the data domain to the decision domain, right? And that abstraction is a learning paradigm, and through that learning paradigm, the system develops its own way of action, or rather, we will say a hypothesis in terms of machine learning. It develops the hypothesis, and there are ways that we can modify the hypothesis, provided we feel that there is a new variety of data for which I need to generate the outcome. So to do that, I can again retrain the system or can generate a sort of change in the hypothesis based on the new type of data. So what I'm trying to focus here is that the machine learning system, machine learning model of approach of building the systems, not only tries to find the best possible outcome or the best possible result based on some known knowledge. Vis-a-vis, it can also scale up, or it can also step up, provided there is some change in the understanding or there is some change in the scenario. So that is the adaptable part of machine learning. So machine learning is a very robust, is a very adaptable technique, and which actually solves the requirement of the various types of complex problems which we try to solve using our artificial systems, computing systems. Classify that is a very naively or a baseline approach of machine learning is something called prediction or classification. Obviously, there is something called clustering, but just to keep on the basics, I will just try to highlight these two issues: what is a prediction and what is a classification. So prediction means that I am getting a set of inputs, and I'm trying to generate the output in terms of a specific value, right? And the value is obviously dependent on the domain. So for example, I can tell that, hey, provided you give me the different parameters in terms of the business of a particular company, right? Maybe the business in terms of their profit, of their loss, of their amount of asset value, number of years the company is existing. So based on all this data, you give me a data, right? I can build a model, and I can predict that what will be the stock value of the particular company. So when I tell the stock value of the company, the value can be maybe from rupees 10 to maybe from some lakhs, right? And it can have any value. Maybe it can have 1,000.50, or it can have a 10,750, something like that. So it can have all possible values within a domain, and that's what is called a prediction. And the prediction problem works very good for the cases where there are forecasting problems, like we want to predict the amount of rainfall, we want to predict the amount of agricultural yield. That means in many of the cases, what this machine learning problem does, they might be missing out with some value, some percentage what actually happened and what they predicted, but that doesn't makes a much difference, because provided you have predicted the rise or the fall in the value, that is sufficient to take more decisions rather than sticking to the actual value, that whether my stock price will be 10,550 or 10,670. Okay, so rather if I tell that okay, it will have a trend like 10,000 to 11,000 to 12,000, and then it will have a fall of again maybe 7,000, 8,000, like this. So this actually gives us a good solution to the problem, and that's why prediction or forecasting helps it. When we try to model this, when we try to understand the problem, the model can be linear or non-linear, which means that whether my function, so prediction or a regression is nothing but a mapping from your input to the output in a functional form, right? And this functional form may be linear functional form, which is easier to evaluate, but in many of the cases, easier functional form doesn't work out. You have to take a nonlinear functional form, which can be a polynomial equation of some degree. There is also something called logistic regression, which I will not explain much here, but logistic regression is something that is a regression, but instead of the continuous range of value, it rather works as a classifier. So what is classifier? I will just try to tell you here. So instead of a prediction problem is one type of problem where your outcome can be a continuous range of values, right? Continuous values within a given range. Vis-a-vis when I tell a classifier can only have some discrete values in its outcome. For example, if I give an image of a tumor, right? Say a brain, right? A brain has some patches, right? And my machine learning algorithm, which is based on computer vision, will tell either this image is for a cancerous patient or a malignant, or this is a malignant patch, or this is a benign patch, which means that my outcome can only have two values, right? And these are called labels, and these values are called class labels if I try to define the problem as classification. So my class label can be, okay, this is a malignant class, or this is a benign class. Right. Obviously, this type of classification is a binary classification. We can step up. We can also have a multi-class problem where we can tell that the particular person or the particular cancerous patch can be of high risk, or can be of medium risk, or can be of low risk. So this way we can increase the class levels also in the classification problem, but in the classification problem the levels are finite, and your outcome will always map to any one of the levels, and that's why the classification and prediction as a type of problem varies, right? So when we are trying to do a prediction, we are trying to generate a function from your input. When you are trying to do a classification, we are trying to predict the boundary between your data set, and that is predicted in the figures which are being illustrated in the slide. Now everything what I try to tell in a nutshell here, obviously, without not taking a full course here, I'm just trying to push you onto the very very basic understanding of this domain in a very precise way. So when we try to look into the prediction or classifications, I've already told something that some of the variables comes into play, right? And these variables are commonly known in terms of machine learning, are commonly assumed or commonly coined as the features. Now the machine learning classification or prediction works pretty good, right? If you have chosen your right features, right? What are the features? What are the variables which actually lead to outcome, right? Or what are the actual features or variables which actually lead to the class levels? If I can do it by some process, if we can do or if we can generate it by some process, then the next task of mine, generating the outcome in forms of prediction or generating a class level in form of classification is very easy. But if we cannot do it, right? If we cannot in a particular problem domain, we cannot extract the features in a very efficient way, or maybe when the model's in under action in the runtime scenario of a model for a particular set of data, okay, it is not possible for me to extract the feature, and then my model fails, and that's what is the cautious about we have to be very cautious about these models when they are working with the features, because in many of the cases abstracting the features in the real-time scenario is pretty difficult, right? And that's what some of the examples has been shown. So due to the lot of effects, the environmental effects, the features are either camouflaged or the features are subsided due to some overlapping of some objects or some scenarios, or due to the environmental conditions. The abstraction of the features are not always in the same form, and that's where taking the right features. So provided you could have saved if you would have taken a feature which is invariant of this particular environmental effect, right? And obviously it depends on the particular problem whether you can have those features, but provided you can have the features which are invariant of the different conditions, then probably you have saved your machine model, right? And that's where I am just pushing towards the concept of deep learning. Why deep learning is so efficient in handling this type of problems. So when we try to focus on the classical machine learning, that means as I have pitched this particular lecture, more biased towards deep learning, I will be quickly sweeping towards the deep learning instead of covering much on machine learning. But what is the way the machine learning, the classical machine learning models works, like the naive classifier or the SVM classifier, or maybe a good regression model, is that you try to first extract the features, right? If you extract the features and then you design your classifier which can work in the feature space. So this is a two-step process where you first understand the features by your own way, and then you develop the classifier based on the features. So sometimes these features are called handcrafted features, in the sense because these are not machine crafted. So machine doesn't have generated the features automatically, right? It is the programmer or the algorithm designer who have analyzed the data and have done some sort of statistical analysis on the data and try to find out that which features are prominent and which features are weak, and based on that he or she has settled on the feature set. But if you look into the scenario, what happens in the deep learning, in the case of deep learning, the motivation is more on representation learning, right? And what is representation learning? Representation learning means the feature represents your data, right? So for example, if you tell me, right, you can tell that, okay, I am a man, right? I am a man of age, some age of X, right? But whether that gives you any information about me, so that suppose you want to take me in your organization and try to find out that whether this person can work in a particular project of machine learning, right? But if you abstract my feature that a man of X age, okay, it doesn't gives you any information about whether this person can work in the project of machine learning. So you see that the inference what you try to generate out of a data and the properties of the data what you abstract has a direct correlation. If you don't abstract the proper information, so proper representation of your data, it doesn't help you to generate your inference or your decision. So now, whether there is a process, whether there is a system process, whether there is an algorithmic process, automated process by which Your machine learning model will try to understand the features which represents your data most efficiently. That process is called representation learning, right? And that representation learning has an evolution path from your classical machine learning to the present day of deep learning. Right, and deep learning is more towards representation learning, whereas the classical machine learning is something where this representation is being done in an independent way by the experts, obviously by the experts, but this is done by their own understanding. It is not the understanding of the inherent algorithm which is trying to learn the representation on its own. And that's where the classical machine learning and the deep learning differs in their work process and in their way the problem is being analyzed. So I will get into this once again, but I will now try to get into that. The deep learning in a very fundamental way. So the deep learning term I am accustomed with the deep learning term not long, right? I'm accustomed with deep learning term only for the last 4 years, right? I started slowly from that. We always have a tendency to work with the things with which you are comfortable. So we are comfortable with machine learning regression models. We are comfortable with the Bayes classifier, then SVM classifier, then ensemble classifiers. We are very comfortable with those, and we are trying to, and we worked in our projects and the PhD students maybe under 2014, 2016, right? And 2014-16, when the new students joined, they actually pushed me, or rather, they pushed us that, sir, there are networks which are coming up in a great way. Then I told that, okay, I know what is a neural network, but what networks you are talking is then told that, sir, we are seeing the deep networks are coming, right? And then that means, and then obviously being the supervisor and being running, that means and trying to work in new areas of computer science. I also jumped into this domain and tried to learn that what is happening. So first of all, when we look into this particular scenario of deep learning, we have to understand why the term is deep, right? There's one part of that means the one aspect of the deep is obviously in terms of the network, which we will see soon. What is that network, right? And this deep in terms of network means it is a deep network indeed, which means that it has multiple layers in the network stacked one after another, which makes a very large chain of processing. Okay, this is one part of the deep part of this. Another part is deep learning. So what does deep learning mean? So deep learning means I have learned deep. What it means? It means that I have learned something which is not so simple to extract. I have learned something from my data which is really a very deep level knowledge, right? And that is also another aspect of deep learning. So what deep learning does, it tries to extract the latent abstraction. So latent abstractions means these abstractions are sufficient enough to represent your data, but these abstractions are not very apparent. Okay, these abstractions are not very apparent to understand. So there's a beautiful picture. I demonstrated that in one of my lectures, but I just forgot to place it here. So the lecture that I will try to describe it, what that particular story tells. That is the image which has been given by one of the MIT profs. That is, I think she's a lady. Okay, yeah. So in her lecture. So that means obviously in the context of machine learning, deep learning. So the picture tells that there is a cave, right? And there are prisoners in the cave, right? And there is a wall in the cave, so that the prisoners cannot see what is happening behind the wall. Okay, so what happens behind the wall? Behind the wall, soldiers move. Okay, soldiers move with different types of okay, say arms and ammunitions, or different types of maybe candles, maybe some stuff. And what this prisoner see? Prisoner sees a shadow of those, because there is a light somewhere in the back of this wall. So the prisoner sees the shadow of the objects which are carried by the soldiers at the back of the wall. So the soldiers, what they're carrying is not apparently visible, but what these prisoners are seeing, they're seeing a shadow of what the soldiers are carrying, and from that some information they captures. But this information is not the exact information. This information is generated by the latent features or latent information which are actually being carried by the soldiers. So this is what is called latent features. So latent features are really deep, or they're high-level features which needs to be extracted to really understand the data, right? If we can understand the data, what we can do, we can tell that, hey, this data is different from this data. So which means it is a sort of classification or clustering the data, right? So that is the way how your latent representation or latent feature extractions or deep feature extraction from your data helps you. Okay, so this is what is trying to say, and that is actually the representation at a higher and a more abstracted level from the raw input are something which is done using multiple stages of the network. You can ask me a question that, sir, why there is so many levels in the network? So many levels in the network is there because in one layer you cannot abstract the entire stuff, right? Suppose I give you some small edges, right? You cannot tell what are these. But if I try to compress the edges, okay, spatially, and then I show you, it will tell, hey, this edges forms a region which is eye. This edges forms a region which is nose. And then we again compress this. Again, we try to bring together the nose and the eyes and this, and then it will tell that, hey, this looks as a feature. So you see that when you try to go into the pixel level, okay, it may be only the edge intensity or the intensity values of the pixel comes up, and by that you can take a decision that this pixel forms an edge or not. If you go to the higher level in the scale, you will tell that, okay, these edges are spatially closed, and then you go much higher into the level, you can tell that, okay, these regions are spatially closed, so this region represents an X object. And that's the way why we require multiple layers. This multiple layers tries to extract the features at different scales, and these scales are pretty important to ultimately to know what this data actually represents, right? And that's what is a complex functions can be learned, or complex representation can be learned through this type of effort, and that's why the network is deep. So provided we understand all this, you can very easily now appreciate this particular illustration, which goes through a walkthrough from your standard AI, which is a rule-based system. It's a logic system. That means if A happens, B happens, then C will happen. Okay, something rule system. So, or if A happens and B doesn't happen, then D happens. So these are rule-based systems, right? And then comes the classical machine learning where features are first extracted from your data, and then features are used to build your predictor or classifiers, and then the classifier or predictor works. This is in the case of representation learning, which is towards the deep learning. What does these features are being learned by your network, through your network, or through some sort of analysis which are performed, right? And one of those analyses will be pretty clear when I go into the discussing details of a deep network. And through this analysis, the features are understood. So the understanding of the features of your data is something called representation learning, right? And then the features are understood, and the features are based on the features the system learns, and system gets generates the model by which it can give the correct output corresponding to the data, right? And that is all the progression from your early AI to the present scenario of AI, which is more towards representation learning and deep learning. Now you can tell me that, okay, it is not that what I'm talking, it was not existing, it just came into the last 10 years. No, it is not. Okay, though we started for the last 5-6 years, but in the computer science domain, this theories existed starting the machine learning or the concept of network. Actually, the concept of network came in early 1950s. But why this that means at the present scenario we see a rush of deep learning activities, because the ecosystem is well developed, right? Ecosystem in terms of data. So this deep networks requires a good amount of data, a good variability of the data, so they can get well trained, and the models can be well built up, so that they serve our purpose. So we have the big data in the various domains. This data has to storage of big data, to access the big data. The standard techniques or technologies in terms of data warehouse and data mining are in place now. Similarly, we have the system resource in terms of hardware. We have resource which can process a large amount of vector data in terms of tensor or in terms of GPU processing, and that immensely speeds up the processing scenario. Last but not the least, we have the platforms. We have a lot of platforms in the open source domain, right? When we work in the domain of machine learning and machine learning and deep learning, obviously we were earlier restricted with some sort of tools, right? I'm not taking the names of the vendor because it's not appropriate to tell that in this point, but we know that there are some vendors which are proprietary tools, and those tools are pretty costly, and it was very difficult for us, basically the academia or on the student level, to work with those tools. But we are lucky enough at the present scenario that we have a lot of open source tools and libraries, basically TensorFlow, Keras, all these, and their total set of Python libraries in the domain of machine learning and deep learning has helped us immensely to practice this domain and to get experience in this domain in a very seamless way. And this all have contributed to develop the ecosystem of why we all can now think deep learning or deep networks is a very good tool in our multiple activities in computer science. So now this part, what I will try to speak is about the fundamentals of your perceptor network, because if you don't understand that, it will be very difficult for us to understand networks which are pretty deep. So I think all of you know it, but just to make the connectivity, I made some slides on this particular concept of perceptor networks. So perceptor networks are very simple. It actually resembles our simple activity which are being done in our nerve cells or neurons. The neurons have synapses through which they collect the data, and then there are some neuron junction points by which the data actually undergoes some transformations and processes and passes on to the next layer of the neurons. So if you only focus on a single neuron, its computation model in terms of artificial neural network or perceptron network is something what I illustrate here. So what I have here a particular nodes in the nodes of a neuron, and these nodes, which are the extreme left, represents our input nodes, right? And the way I label the input nodes is dependent on the number of variables or features I am accepting at my input, and that's why I have labeled them as x1 to x2, and you can extend them up to xm. That is, I have kept one node very different from the other, and I have made it a static value 1, right? Why I will explain it very soon. For the next understanding here is that for each node which comes into the next node of the next internal node of your neuron, each of your inputs are actually connected with weight edges. So the edges means information flow, but this information flow is based on the weights. So what this actually means that this input will be multiplied by the weights, okay, which I assign in the edges, and that will form a cumulative flow towards this node. So the cumulative flow towards this node can be well represented by the term xi multiplied over wi, Xi's are your input and Wi's are the corresponding weights, and it goes over all the inputs in this particular neuron. So now it is pretty easy to understand why I have kept this particular as 1, because this weight is not a weight in the actual sense of the input weights. This weight is rather than a bias. Just to make the network very regular, I have made it as an input and I put the weight as W0, but this W0 is different from this particular Wi because this Wi are adjusted based on the inputs, but this W0 is a parameter of your model. So that's where these two W differs, right? This is a very small understanding, but this understanding is very important. So this bias is for your model, and these weights are based on your data. You need to train that, okay, based on that, okay. So now what happens here? This summation actually sums. So this cumulative summation with the bias gets a total cumulative data, the cumulative value, and this cumulative value goes to an activation layer, and this activation layer here is represented as a function which is W1 or maybe in terms of mathematical function, it can be that it's operated by a function g, which is nonlinear. Why it is nonlinear, I will again come to that part very soon. So this nonlinear function works on this cumulative weights multiplied with inputs plus bias, and this nonlinear function acts on that, and it generates an outcome y, which is the outcome of this particular node. Right, and this outcome may be a prediction outcome, or this outcome may be a classifier outcome, provided we have trained this network with some good amount of data, and we have settled down what will be my Wi's and what will be my W0. Right, I will. That means I think it will be pretty clear when I go into the next level and next discussions. But before going to that next discussion, it can be well represented by a computational function, which is something like this. The X can be represented as a vector, W can be represented as a vector, and we can just represent this in terms of an algebraic form, which is nothing but X transpose W and some with W0, and then it works on the activation function. Now, as I told that. What is this activation function? Why it is actually required, right? This activation functions, if you see the classical book, they are called the firing functions. Why firing functions? Because it is a sort of decision function. So you take your inputs, right? And this is very important. That means many of the people, many of us miss this understanding. But this understanding is again very simple, but is very important to understand. So each of the neuron has a contribution to your decision. Now the contribution to the decision again depends on the input what the neuron gets. So the outcome what a neuron generates is dependent on its input, and the input is nothing but weights multiplied by the inputs, true inputs by the bias. And this cumulative goes to a neuron, and on that activation function it comes up. Now, if this cumulative is a common activation function, which is a sigmoid function, what it tries to tell is something it tries to tell that it actually squashes. It also called a squashing function. So squashing function means it either puts it into one extreme or it pushes up to another extreme. So if a value of my cumulative value is just over this value, it will squash it to 1. If my cumulative value is just a certain below to 0, it squashes. Okay, it squashes to 0. And just a similar function, which is a hyperbolic tangent, tan H function, which instead of squashing between 0 and 1, it squashes between -1 to +1. And sometimes it helps to normalize your network in a better way because it has both negative and positive values. The important activation function in terms of deep network is ReLU, or rectified linear union. Why it is important? Because ReLU is the default activation functions in our deep network. how ReLU differs with this particular with the other switching functions is something like this. In the ReLU, the function is represented by max of 0 and z. So the max and 0 and z, which means that if a function is lower than 0, that means if the outcome is lower than 0, that means if your input is lower than 0, then this particular activation function will always give 0, because it is max of 0 and z. So if your z is negative, then your 0 is the maximum, so your outcome will be always 0. Vis-a-vis, if your outcome is above 0, then this activation function will give it as the outcome. So it is something like a function which is 0 for all the values lower than 0, and which is a sort of ramp function for all the values which are positive. And now I can just have a discussion or to let you know that what makes ReLU different from this from the other functions, and that will automatically answer that why ReLU is also preferred. Okay. So first of all, to understand this, you have to look into the derivative of the functions. The derivative of the functions are being plotted also in another plot, right? Now it is very easy for us to understand that all these functions are nonlinear functions. Why these functions are nonlinear functions? This is again a question which comes from the student level. That sir, please explain us why it is a nonlinear function. It is a nonlinear function because its slope changes. Any function is nonlinear if its slope changes. In a case of linear function, its slope is constant. So its slope changes, that's why it's linear. Now there's also a bit confusion that sir, why ReLU is nonlinear? Because ReLU is piecewise linear. I tell them, yeah, it's correct. ReLU is piecewise linear because ReLU is linear here and ReLU is linear here. But ReLU is still nonlinear because it still has a change in the slope. So it is a special nonlinearity which is being imbibed in ReLU, but in terms of function, it is nonlinear because its slope changes. Though it changes only once, but still the slope changes, so it's nonlinear. Secondly, what is the difference between these two functions? So the difference between these two functions is basically a problem called a vanishing gradient problem. So what is a vanishing gradient problem? The vanishing gradient problem is that your outcome doesn't change as much with the variation of your input. So your outcome is something which depends on your input, but your outcome doesn't changes. And that is actually the derivative, right? That means how your input influences your function. So it is a derivative of your y in terms of x. But if you see both the cases in this region and in this region, in both the cases you see the function saturates, right? And as the function saturates, you cannot distinguish the outcome for an input which is here vis-a-vis an input which is here, or vis-a-vis an input which is much higher than this. So for all those, the outcome remains the same. So it means that it is a saturation function, both in the high level and in the low level values of both the corners value of your input, and that makes a pretty difficult to understand or to change your weights to adjust your network. Vis-a-vis what a ReLU does, that means ReLU for the outcomes which I am taking. So the outcomes which I am taking means for the outcomes where my firing function or activation function gives the value. Okay, it's obviously for the inputs which are greater than 0, my activation function will give a value. And for all these values of z, I have a unique value of my activation function, which means that this function never saturates. This function can always distinguish between an input 2 and an input 3 or an input 5 and an input 10, because ultimately there will be a difference in the outcome for all these inputs. Now obviously we know that when we look into the ReLU, it actually collapses everything which is below 0 or negative. That means it is a good approximation, but sometimes we we might need to explore. That means some contribution or some negative contribution we need to expect out of the values which resulted to negative inputs. And for that, there is something called leaky ReLU. So in the case of leaky ReLU, what it does, it actually uses a weight or an adaptive function, which is something like 0.01 of x when x is lesser than 0. When x is lower than 0, we actually there's a scale factor of 0.01. You can adjust with that. So what it does, it tells that your outcome will be slowly vary, not actually vary in the same rate as the data, that is as your data, but it will slowly vary, but it will still give a variation in the negative zones of the data. So this also helps in sometimes to understand that what is the influence of the data which didn't create a positive impact but a negative impact on my process, on my decision. And obviously there is something called softmax, which is a sort of probabilistic outcome, which actually generates a probability of all the possible outcomes that will add below, and then the outcome for which you are measuring, right? And that is called a softmax, which will be also used in our networks either in the classifier level as an activation function. And these are the common activation functions, and these are the common philosophy of the activation functions in a gross way. Now you can ask me that, sir, why we go for nonlinear activation functions, why it is required. It is required because nonlinear activation functions map the data from the input domain to the decision domain in a nonlinear way. And that means, and this is very important because many of our decision problems have a nonlinear class boundary instead of a linear class boundary. So linear class boundary cannot solve the problem. So we have to project the data to the inference in a nonlinear way, and that helps to solve many of our problems. And your nonlinear activation function actually does that job. That means from your input, the data coming from the input neurons, it generates a decision function which is a nonlinear, and that exactly maps the decision, most of the common decision problems, which are nonlinear decision problems, and that's why nonlinearity is preferred. Now, from the single network, we can move on to a multi-layer network, and the assumptions are same. Only the thing is that for multi-layer network, as your hidden layer will also have multiple nodes, and each nodes will be connected with the inputs. So what we had the picture for a single perceptron was that the set of inputs will migrate to only one node, right? Instead of that, what we do is all inputs will combine with each of the nodes in the hidden layer. So for the case of hidden layers, it is a generic equation. It is a multiplication of your multiplication of your wji xj. So this j is the index of the z what we are trying to evaluate. This i. Xj's are the inputs, and this i is the index of the I. So for the Z1, this index will be 1, and you're computing for Z1. So bias will be different from Z1 because it is W01, and weights will be different for Z1 because this is WJ1. Similarly for Z2, this I index will change to 2. And this way we will first evaluate all the Zs. Now these Zs will again serve as an input for the final outcome, which will go to the activation layer. And that's why we will tell for each Y kappa is your outcome. For each Y kappa, it is a particular Zi will come up. So for a particular Zi, we will have this particular, that means a particular Zi, that means this Zi's will be connected with the Y kappa. So we have the weights in the final layer which are now combined with this Z, the Z value, the values which are appearing at the Z node. And that's why we are combining the weights in this layer, which are Wji. This I is again for the particular outcome. Maybe for Y1 it will be Wji, and this will be done for all the Zs which are in the hidden layer, right? And this way you can go on increasing the hidden layer. Obviously, the connectivity what I show here maybe different way. You may have different ways of connectivities, but accordingly, that means if we drop some connectivities, there will be the weight and the input numbers will change in different layers. But if we have a fully connected network in all the layers, then this is the scenario what happens in the fully connected layer. Okay, and this way, from a single perceptron model, you can go to multi-layer perceptron model, and you can go ahead. So last but not the least, what is the role of the weights and biases? And okay, now it will be pretty clear if you can understand this discussion. So what happens in the case of weights? The weights are being decided by your training data. So you need to train your neural network, right? And suppose this is your training data. What it tells, this tells that provided you give the input 1.3, 3.7, and 2.9, your output should be 0. But obviously, as you have started with some random weights, okay, your output will not be 0 initially. Your output will be something maybe 0.8, and then you measure the error. By knowing the error, there's a technique called backpropagation, which I'm not getting into extensively due to the limitation of time. Using the backpropagation, what you try to do, you try to adjust these weights, and adjusting these weights actually tries to make your outcome very close to the values what your training data gives. And provided you have done it very efficiently or very closely, you can tell my network is stabilized, and then it can work with some new data, and then it can give generate the outcome pretty accurately for new set of data. Okay, and that's what's the role of weights. So weights require adjustments, and these adjustments are done using the training data to meet the accuracy or the training accuracy okay, for the given training data set. Now what happens in the case of the biases? So what the biases does, as you see that biases are an input, which is something like W0. So W0 is always there as an input, right? Provided some input comes from your actual nodes, okay, like Xi's or not. So this W0 determines the point from where this activation function switches. So for example, if we shift the biases from the negative to the positive, what we're actually shifting, we're shifting the point where the activation function switches. So in this case, in these three curves, nothing is different. There is no change in activation function, but the way the outcome is generated is pretty different, because for this case, you see, for this case, okay, for maybe for the middle curve, we try to understand. For the middle curve, 0 is, that means something here is sufficient to switch, or maybe something sufficient to switch. But in this case, though the curve is same, the same value will not at all switch. The same value will still be in the low level. And for this case, and if you compare the curve between the left one and the middle one, you see that the curve in the middle one, for a value which is maybe minus one, it will go to the lower level. But for the case of this curve, a -1 will shoot the value to very high. So you see that whether the value will be shoot to high or low, that means depending on the switching of the activation function, it is controlled by the weights, which actually controls the switching of the activation function. So in the summary, I tried to explain all of you that what is the role of weights and biases in my network, right? And provided you understand this, that means I will just quickly. That means what I can do. I can just take a. I don't know whether I have a. Okay. So let's actually finish this part, and I'll go to the questions next. After 2 slides, I have the question slide. So provided we understand the perceptron network, based on that, the deep networks comes up, right? And the fundamental deep network is actually called a convolution neural network. And the term convolution is a pretty important, and what it is, I will just try to tell you soon. But before that, you have to understand that the convolution neural network, that means if we try to progress from the neural network to the convolution neural network, the neural network actually works on a vector data of the inputs. right? And vector is a single dimensional vector is the most simple assumption. So a single dimensional vector assumption is pretty good for the data which are based on the time samples. So each time is a one dimension. So time is a dimension, and based on the time you record the data. So this is one dimensional data. But when you go get into the data like an image, it's a two dimensional data because you have to tell the two coordinates of your data. One coordinate is your x, and one coordinate is your y. So these are the spatial coordinates of your data, and based on that you take the data. So this data becomes a two-dimensional data. So from the 1D information from the simplistic view of 1D data or a 1D vector of it gets into your network. When you step up to the convolution neural network, you have to just expand the ideas, and you have to just think in terms of a two-dimensional data. Right, and that means this x. Okay, that means your x are not only taken from y dimension. The nodes are not taken only from one dimension. It's also taken from two dimensions. Right, and just to visualize that, if we try to work on the window data, right? We worked on a sample size, right? I mean, how it looks like, how the neural network model and the convolution network model is actually the same. Okay, I try to establish here that the neural network, what we understood there, and the convolution, what is being performed in the convolution neural network, is exactly the same thing what we're doing. Only the thing is that the weights what we have done in the neural network are nothing but the weights of your convolution function. So how it happens, let's try to understand. So these are your neurons, like x1 to x0 to x1, right? And what you're trying to do as your data has a dimension, right? You go into a window. Okay, this is a linear 1D data. So what do? We try to take x0 and x1 and x2, x3 and x4 and x5 like this we do, and we try to combine them with the weights. Right, and here is the activation function which comes here, and this activation function actually generates your outcome. So now this combination of W0 with x0 and W1 with x1, okay, and similarly W0 with x1, W1 with x2 is something what we are doing. We are actually convoluting a kernel, okay, which have the values of W0, W1 with the vector which has been defined by the values x0 to x8. How it happens, let's try to see it, right? So what we try to do, we try to first of all try to make it very simple. So we try to tell that, okay, W0, what is W0? W0 is something like W0 x0 plus W1 x1, and obviously we can expect a bias here. Okay, the bias may be W minus B for this entire layer. So now if we try to represent it a different way, what do? We try to do it in a way that this is nothing but W00 x0, W01 x1. So what it tries to mean is that this particular W0 is nothing but the 00 element pretty well represented as a matrix, and this matrix elements gets multiplied with my data elements which are arranged in 1D, and it can be also arranged in 2D. And this weight elements gets multiplied with the data elements of the neuron, which are nothing but data elements, and tries to form a matrix computation, right? And this matrix computation is nothing but the convolution function what we are trying to do. So this matrix now can sweep over. If we now expand this, instead of this number of nodes, it can be a large number of nodes. So what do we try to do? We try to, depending on the size of the matrix, it will just move over 8 nodes at a set, and it will try to operate the same operation over those nodes in a window of size 8. Right, and it will try to generate the outcome which is y0, right? And that exactly happens in the convolution network, and that's why convolution is called a convolution neural network, because the neural network operations, what is done is now being partitioned into spatial windows, and in spatial windows the weight vectors which were there in my neural network assumption is now converted to a matrix of two-dimensional matrix, and it's convolved over the window of my information, of my data set, and that convolution is very same as that the weight multiplied by the inputs, right? And that's the fundamental of convolution neural network, right? And now I can stop and I can just take a couple of questions from all of you. If there are any questions, I will be very happy to answer. Okay, on to the first part.
Hello. You can share the questions in the YouTube chat as well as the questions on the Google Meet chat. If you have any questions on sir. So please free to share the questions. Sir, a question came from Pallav Pal. He asked that why we use ReLU function in between the network, and at the time of final output, we generally use sigmoid function. Why?
Okay, that's a good question. So what is done? ReLU function is more a discriminator, right? If you see the ReLU function, so ReLU function just tries to do a normalization. Normalization in the sense that the neurons which are not contributing enough or which are not having a value higher than 0, they're just pushed to 0 so that they are not considered in the next level of feature extraction, because it doesn't generate enough feature values for the low level features. Now when we go to the last level, it's more a classification. So normally the networks actually does a feature extraction and classification. So ReLU works pretty fine when we try to do a feature extraction. But as classification tries to give a probability of that means of different expectations, right? Instead of a ReLU, the sigmoid functions or probabilistic softmax function gives a better value in terms of probabilistic score. ReLU is more a sort of threshold function or a normalization function which tries to squeeze everything below 0 as 0, and everything higher than 0 keeps it in the normal value, so that it can contribute. That means it can filter out that which of the feature values are contributing to the next stage and which are not. Yeah.
Okay. Sir, the next question is from Professor Partha Ghosh. So, how will I decide the number of hidden layers and number of nodes in hidden layers?
Okay, that is your model parameters, right? And a number of nodes in the hidden layers is obviously decided by the way we want to find the. We can do some random dropouts, right? There are techniques by which we can do some random dropouts, and we can reduce the particular nodes. So we try to there is no specific way I can pick and choose a node I can drop, but there are techniques by which we can actually do a sort of statistical way of dropping out some of the nodes, and we can see that whether dropping off of the nodes reduces the performance or not. But it is seen that in the many deep networks, the dropout factor of around 0.4, like for the case of ResNet, in the case of VGGNet, people works with a dropout value of 0.4 and still it pretty good. So if you're dropping out the node, you are actually making the data more regularized. So there's something which we didn't discuss much in the particular scope. So when we try to fit your model very, very efficiently with your training data, right? Obviously, it is very good in terms of training. But it is something called overfitting, because in the case of your test data, okay, your test data will vary with your training data, and this variation might not be accommodated properly if you have done an overfitting. So sometimes it is preferred that in training data you keep a scope of error. Okay, and that is done by the dropout nodes, and this dropout node helps in two cases. One case, it actually reduces the training or the backpropagation cost of your network, and vis-a-vis it also makes the network very generalized and doesn't lead to overfitting.
So the next question is from Shobik Mujumdar. He is asking that what do you think on any AI solution, bigger scale implementation of AI solution, and if is there any constraints there?
Oh, bigger scale is a pretty difficult to tell. What is the bigger scale means, that whether you want to work with the data of all population in the world or that scale. So see, that means theoretically there is no problem in the scale in the AI, right? AI can actually work with the data what you give, but obviously our restriction is that in terms of the resources we require to and the time we take to train the data with a large amount of data set. So obviously for any AI model, that means if I can offer the larger and larger data set, okay, it will be better. In terms of larger problem, if you are telling the problem has a high complexity, okay, that is very difficult because obviously our brain is still the most complex processing engine in the world, right? And it is being understood that the latest computational technique is around, that means maybe still 8 months baby's intelligence. So we are still miles ahead to, that means miles behind the brain's computing capability. And but that's all we have is the most complex problem in the world. And but machine learning problem. I mean, there's a big confusion whether machine learning networks can solve the NP problems. The machine learning works on heuristics, so it doesn't fit into the same algorithmic categories where your classical algorithm analysis works out.
So the next question is from Bachu Paul. He's asking that how time series data can be fed into CNN, like audio data or something, whether it can be fed or not into CNN.
It will be understood once I go to the CNN. So what I will do, I will stop this session. I will stop discussing the questions. I will come back to this and let me go to the CNN, and then the things will be pretty clear, I think, to all of you. Okay?
Thank you. Okay.
Yeah. Okay. So let me go back to my presentation. Yeah, and I hope that it is visible, right? So this is what is this visible, my screen?
Yes.
Okay, great.
Yes,
so fine. So let's try to see with a toy example that how a convolution neural network works, and that can be very interesting to all of you. So this neural network is the way the convolution neural network works is very simple to identifying the patterns in the images, and I will try to show you that why patterns in the images, finding patterns in the images is still a complex, it's not so easy problem in a real case, right? So suppose the problem is something like this. That means we give a pattern and we try to differentiate it between X and O. Now this is pretty simple if we give the pattern in this way, because this pattern is a pretty good pattern. You can just do some sort of estimation of your pixel templates, and you can just generate a template of pattern X and pattern O, and you can just tell that, hey, I have done it very easily. But it's not a simple case because in terms of pattern, if we just try to modify it a bit, so the same pattern X is being modified, though it is same X, but it is modified in terms of some geometrical transformations, right? And this geometrical transformation, though in a naked eye, it is fine for us to tell it is an X and it is an O, but the computational algorithm which actually works with some sort of template matching type of stuff will not able to answer that whether this is also X or this is also X or this is also X or this is also X, because it will find there's a lot of difference between the template as a single feature, right? So what we need to look into, instead of looking X as a single feature, we try to find that what are the sub features in the X which actually identifies X, and that will give us a more that will give us a path to distinguish between the different forms of X, but still they are X, right? And that's what CNN discovers, okay? And that I will try to discuss here. So see that this X and this X, this is a rotated X and this is a normal X. Though by naked eye it both are X, for template matching algorithm, it will not. They will not be similar because they will find there are a lot of dissimilarities in the data. So in terms of data, what I try to make the thing easier, I make all the blacks as -1 and all the whites as +1. Provided we do this, if we compare these two data, we will find that mode are reds. So this red means where they differs. So you see that in the case of the exact matching of the two patterns, there is much difference. But what is there that my naked eye still tells that this is X and this is X? Because my naked eye works on not only on larger patterns, but my naked eye also works with smaller patterns. And that's what we need to extract. So to identify this as these two not same, but where it is same. It is same. It is obviously same when we look into the patterns which are hidden inside this in the image. And if we see the patterns which are hidden inside this image, we will see that they have exactly same sub-patterns. So instead of a single pattern, we now go into the sub-patterns, okay, or more deep features of a pattern. So understanding those deep features will tell that, hey, this X and this pattern has a feature which is similar here because both two diagonals are white. Here is a feature which is very similar, where the corners are white and the center are white, and similarly this and this. So every features are very similar to one another. Every sub-pattern of this X and this X are very similar to one another, and that makes a fantastic proposition that these two are same. Now we can do it in terms of our network, provided we can churn out these particular features out of these patterns, and we can tell that they're the same. So to churn out these particular patterns, what we need to do here, we need to have kernels. Okay, these kernels are nothing but convolution kernels, right? And these kernels are nothing but your kernels which are having the weights, right? And these weights will combine with your input data or input pattern image, and we'll try to churn out something, try to maximize and try to minimize something, and that's what's the convolution outcome. If it maximizes, then the pattern is identified. If it minimizes, you tell the pattern is not identified. So the contribution of that particular image patch for the particular pattern is 0, whereas for the pattern gets matched, the contribution of the image patch contribution to the patterns to this particular kernel pattern is high, which tells that this feature exists, and this is the way how we can build the feature space. So feature space is explored by the convolution kernels, okay, and this convolution kernels develops the feature space in each convolution, in each layer of convolution operation, and that's why I tell what is the understanding of layering. I told what is the understanding of layering in the convolution network. It will be clear in my lecture, and that's what I want to place to all of you. So how it happens? So this particular convolution kernel, okay, and these are your neurons, right? These are your neurons having the different values. So this convolution kernel operates on a set of neurons. So instead of all the neurons at a shot, okay, it tries to work on a window of neurons, okay, and tries to do the same thing, okay, and tries to do the same thing, which will be weights multiplied by the inputs. Perfect. And we will find that is the what outcome it generates. And this particular kernel will not only search this in this patch, but it will try to search on and will try to slide across the image, and will try to search the pattern try to search the pattern in the entire image, and will try to pick up that in which spatial region these patterns, that the pattern matching to this kernel will give a high value. And similarly for these kernels also. So I will try to explain for one kernel, and automatically the other things will be very simple to you. So you try to understand the work of one kernel. So this is your kernel, and this is the patch on which the kernel is convolving, or you can also tell that in terms of pretty simple neural network, it is doing the weights multiplied by the input values. So these are the input neurons. So the input values multiplied by the weights. And what it will do, it will just try to multiply each input with each corresponding weights, and see what happens. Okay, I will just move it first, and you will see it happens all one. Right, and then and then we can just take a cumulative score, which is a summation of the score, and try to give try to do an average and try to place a value 1 here. So you see that this particular convolution kernel generates a value 1, which means that this convolution kernel feature and then the feature in the image patch is exactly good, is exactly matched. But it might not be good in some other region. Say if the kernel wants to operate here and it tries to evaluate the same value, same convolution outcome, it will not give the good value. It will give a value of 0.55, which means that this kernel feature and this particular image patch doesn't have a matching at the feature space. So in this way, we can generate a convolution outcome for one particular kernel, right? And that actually can be drafted. The points, the values where it generates a high value, it means that the kernel feature has been extracted, and where it goes a low value, it means kernel feature is not extracted, or the feature doesn't exist in the particular sub patch, right? And obviously there's a computation by which I can tell that the size of the convolution outcome. Okay, it depends on multiple factors, right? Obviously, it depends on the size of the entire image, size of the feature kernel, and also there is something called number of padding layers and the way we slide on the kernel, whether we go slide 1 by 1 or we go slide with a hopping, and that gives the stride interval, right? And based on that, you can compute the value of the convolution outcome matrix as C, and the original image matrix as I, and the filter matrix as phi as F, and then the padding layer P and S. And if you compute all of this, for this case, your padding value is 0, your stride length is 1, so it will evaluate to 7. Your I is 9, and your F is 3, so it will evaluate to 7, and you can come with a 7. So what it does, a convolution generally reduces the size of the data if you don't use any padding. If you have used the padding, which means that you actually covered all the that is the one outer layer you generate, and you push them with all values of 0, then you could have generated the same matrix with the size same as that of the image. So when we tell that you reduce the size and the convolution outcome, it means that you are not using the padding data, right? And this can be done for all the kernels, right? I have used a toy example where I have shown 3 kernels and 3 kernels generating 3 convolution outcomes. But if you see the networks which are there, you will see the kernels of the size 64, 128, and so on, right? And so if you have the kernels like this, and so you generate this, and this is the way you choose the stride on this. Okay, I will just quickly move on to the pooling layer, the max pooling layer. What it does, it actually reduces the subsamples the kernel outcome, right? Why? It actually tries to form a window and tries to take the maximum value of the window as it is the maximum pooling. In some cases, you can also do an average pooling, where instead of taking the maximum value, it takes the average value in this particular window. So how this pooling helps? Pooling helps in 2 ways. One, it is subsample, so that the amount of data, it concentrates the feature space, and it helps to work on a smaller chunk of data for the next layer. Second work, what it does, it actually tries to get the data which is invariant of small spatial changes. So small spatial changes means if there's a little bit of spatial change, this one would have been here or here or here. But wherever one would have been here or here, still it would have resulted to 1 because I'm taking the maximum value of this window. So this means that this particular network, this particular pooling layer subsamples the space and also tries to make your network invariant of small spatial deviations in the patterns, right? And this goes on and goes on, and this pooling will be again done for the 3 convolution outcomes, and it will generate a much concentrated feature space. Before the pooling layer, you could have done. You can do a ReLU also. That means, as we already know what is a ReLU. ReLU actually just makes all the negative to 0, and whatever positive value it remains. So what it does, it actually forces to many value zeros which are negative and keeps all other values. So in some cases you can push. You can have a ReLU before the max pool to further make the data very well normalized and try to only highlight the outcomes which has given a good positive result. So in a sense, this is a normal structure. You can do a convolution followed by a ReLU which normalizes this a bit and tries to explore more the positive values of your network outcome and suppress the negative values. And then you can do a pooling which again compresses the feature space. Right, and this network goes on and you can go on building. So the feature space created by layer 1 will be now explored by feature 2 to generate the next level of features, right? And this way it will go on and it will come up to a level which is something like this. That means a very, very concentrated representation of your feature data. Once we have it, the last stage, we can now have a full go, and we can now expand it in form of a vector. Right? And this is called flattening the network, right? We just flatten. It's called a flattened layer, and we try to generate this two-dimensional representation or the feature representation into a flattened or a vector representation, right? And this vector representation can actually, in a trained form, can actually generate the scores for the different patterns by putting different appropriate weights for the appropriate neurons, so the weight vectors cumulates to the pattern X, and similarly a weight vector, another sort of weight vector will cumulate for the pattern O, and this will be done for all the patterns for which we design this particular network. So this is a sort of voting mechanism which tells that a particular pattern which gets a maximum vote or a maximum score will be the pattern which is being recognized, right? And this is actually done by a prediction mechanism which is called a softmax layer. So how it works out? So suppose during the training set, during the training of the network, right? You have settled that these are the vector values. These are the vector values for the pattern X, and you have settled it in the training. So you sum it, you will get a value of something like 5. Now this is your training data set. This is your input data. Now for your input data, you again come to the same point of the network, and you evaluate the data available in the cells. You sum the data available in the cell, right? And you get a score of 4.56. So you divide the 4.56 from the data which you have generated by training the network or settling down the network, and that is 5, and then you generate the score for 0.91. Similarly, when we try to do it for the other pattern, okay, and we are trying to find it whether it is vector for O, whether it's vector for O or not. So in my training data set, my vector for O value was something like this, right? And if we try to do the cumulative sum of those particular values in the input pattern, which is X, okay, if I divide it with this, I will find the value which is 2.07, right? And these values are basically values which are being generated to combining the input with the weight values, right? And so the weight values in the softmax layer will actually, that means in the dense layer before the softmax layer, the multi-layer perceptron layer in the softmax layer will actually try to generate the different types of probabilistic categories for the different patterns we are trying to classify using my network, right? And this is the way the networks are stacked, and we have a multi-layer perceptron, dense layer in the end, followed by a softmax layer, and that actually generates a full network at a show. So this is what happens in the network. So you have an input pattern, it goes to the number of convolution channels. So the channels are nothing but filters, right? The channels, if you see, and then we have, so this is a 24 N1. So it means that you have a 24 cross 24 image. So your image input size, your data input size is a matrix of 24 cross 24, and you have N1 channels, which means that it is operated by N1 convolution kernels. And this is the way the entire network is represented, and ultimately you have a flattened network and then a softmax layer. In some cases, as I told, you can drop out the nodes just to make the make the network a bit relaxed and a bit adjustable with the different types of data in the real test scenarios. So I will just quickly try to close, and then I will take the questions due to the limitation of time. I will not keeping the questions here. I will try to finish my lecture, and then I will open to the questions, right? And so if you go to the image in a real sense, what I shown in the image in a real sense is fine, but you can tell me that what happens if it's a 2 RGB image. So if it's a 2 RGB image, what I have shown is 24x24, or what is the dimension of your image matrix, it will be, instead of only one channel, it will be done on 3 channels. And that's the extra computation or extra thing you have to take care if you are doing with a color image, right? And the way it is done is something you can just try to visualize this as a sort of cube. Why it is a cube? Because these are this volume, these 3 channels generates a volume, right? And the height and the width is depending on the resolution or the amount of image size you are taking. So amount of image size you are taking defines your height and width of this cube, and the depth of the cube is depending on the channels. Now, in terms of channel, obviously the simpler way is RGB. Sometimes people work with the GIS image where you have different spectral resolutions are being taken in the different frequency component, and that also you can use in your convolution kernel space by adding more layers in your depth wise, right? So that is the ways you have to just do adjustment based on the color image. But the most common is the RGB space, which has 3 channels, and you have a depth of 3 in your input, right? So for your RGB, obviously it's convolution outcome will be done with a cumulative effect of the filters on each of the image red, green, and blue information, and this is the way you can do a cumulative operation, and you can do a cumulative output of coming out from 3 channels, and that you can record as your convolution outcome. Okay, so now these are the simple things. What are the, as I think somebody have asked, someone asked me that how you settle all these things, parameters. This is a simple way how we settle the parameters. So the way we try to do is that your 6x6x3 is something like you have a 6x6 dimension of your info image, and 3 is a number of that we RGB, and now it has been acted by 3x3 filters, right? 3x3x3. So you have a 3x3 kernel, but this kernel will also be of dimension 3 because it is working on each layer. So the number of parameters for each filter. Okay, these are the weight parameters, right? You try to think the W0, W1. So number of parameters for each filter is 3x3x3 is 27. And there will be a bias term for each filter. So bias term will add a particular value, 27 plus 1, 28. So there are 28 parameters of each filter in each layer. And now if we have 10 filters, okay, I mean the number of channels you have, a number of convolution, so the number of convolution kernels you have, so N1, N2, N2, something like this. So number of convolution kernels you have, so based on that you have, suppose for example, I have 10 filters. So the number of parameters you have to adjust in one layer is 28 start 10, right? And it goes into million parameters because what happens is that this number of these filters, the number of filters goes on to 128, 256, and something like that, and it's exorbitant, and then it gets adds up in each layer because each layer has the same amount of dimension, and again this way it works out, and so you see the pretty large number of parameters you have to adjust, and these are all adjusted by your technique called backpropagation, which pretty efficiently works for your deep networks also. The limitation of time, I cannot expand fully the deep network. I'm just trying to give you some of the important things to understand the key ideas of your deep network, and try to give you a very summarized way of how to visualize the number of parameters which actually generates in your network, in each layer. So this is something where it is done, that the way it grows up is something like this. You'll see that 32 equals 32 equals 3 equals 28 equals 28 equals 6, and that is the way it goes to 14 million. That's a large number of stuff, right? In the case of a normal neural network, right? But when we see the convolution neural network, okay, it's a bit different, right? So this is what it does in the case of a normal network. So a normal network, if we have 32 plus 32 plus 3 data space, okay, and if you are 28 plus 28 plus 6 is your number of that means your number of neurons are connected by your weights, you have so much large parameters. Whereas in the case of convolutional neural network, what it does, it actually separates the data into some spatial blocks, right? So instead of multiplication, it becomes addition of the parameter data, right? And that makes a big sense. So what it does, it starts with 5 plus 5 plus 1, because you have a kernel of 5 plus 5. So instead of the kernel working on the entire data set, which may be 28 plus 28 data set, instead of doing that, it is working on patches. So it works on 5 star 5 and with one bias parameter 1, and maybe you are having six kernels. So the number of kernels are same, but in the case of a normal neural network, as it works on the entire data space, the number of parameters gets pretty high. In the case of convolutions, in the case of CNN, as the space is fragmented into the patches, the number of parameters becomes much less. So you see that's the way you can control your network, and you can train your network with a much lesser parameter in the convolution networks compared to what we have in your normal neural network if you want to do the same thing in neural network. And secondly, the neural network doesn't preserve the spatial correlation between the data, right? And I will just quickly, I will not, due to the time, I will not go into much of this. These are the very good important networks which are there available in the present sets, and you can go to some of the very good work available references, and each of the networks have their well-defined dimensions and parameters, and they are available in the code in the GitHub also. You can look into those. It's a very interesting to start point of your studying the deep convolution neural networks. I'm not going into much. I've already discussed this: convolution, pooling, and fully connected, how we try, what are the parameters we try to do, what are the knobs we try to work out, and these are all we try to do. And when you try to build a CNN model, that means there are different steps. Obviously, you need to prepare the data, you need to normalize the data. Normalize the data means you need to have because normalization is required because the data can be very varied. Okay, data of temperature, maybe from say it's a minus 52 plus 60. Okay, data of your chemical composition of your soil, maybe from 0.1 milligram. So nitrogen content in the soil maybe 0.1 milligram to maybe 0.5 milligrams. So your data are in a different scales. So you have to normalize the data to bring the data in the same order, and then we train the network, and then we try to evaluate the error, which is the loss function, and then you try to repeat the process of training, in terms of batch, in terms of epoch, and that trains the network to the perfect way, and then your network is ready to go, right? And obviously, it's not only images. As I told, convolutional network can also work on sounds, okay, where we can actually see the frequencies as a one dimension, and the time steps in which the different frequencies occurred. The time can be another dimension, and that can also represent a particular feature space, data space on which you can very aptly do the convolutional neural network, right? And last, I'm just telling that obviously I will invite all of you to the research what I'm doing in our department. That is Ekechudri School of Information Technology. We have a formal data science group and data science lab in our department. We are working with a number of projects, very interesting projects. Students and faculties are there working on computer vision, which is my very pretty early research activities, and video analytics is there. We are working with some very interesting problem in the domain of sports analytics and surveillance and security. We are working on renewable energy with a collaboration from National Institute of Wind Energy. We are trying to forecast the renewable energy models, that means the source models. and it's also funded by USAID, which is a collaboration with the Department of Statistics of our university. We are working with text analytics with some of the corporates. We are working with cybersecurity with some of the industries, and we are trying to do analysis. Also, we have a defense project in this line. We have recently, for the past 2 years, we have started the domain of quantum-inspired machine learning. A couple of people, senior people from industry, have joined us, and we have a funded project with the Dear State Indo-Japan collaboration with one of the Japanese university, and we are trying to we are developing some good techniques in this domain. And so thank you all, and this is the last but not the least. This is a conference with the people, the faculties interested research here. We are hosting this in Kolkata. But that means we booked the Science City auditorium, but I think probably we will do it in the virtual mode this January. This is the biggest conference in India on analytics, and this time we have brought it to Kolkata. We have strong industry partners, TCS, IBM, this time IIT Guwahati and NIT Durgapur are the academic collaborators of this particular conference. And the web page is all there. You can go to icdmi.org. We have fascinating speakers, keynote speakers from IEEE fellows to big persons in the industry. We have industry chairs from Intel and Ericsson, and they are trying their best to motivate this. In this pandemic scenario, obviously to run a good conference is a challenge, but we're trying best to do that. And I invite all of you to be a part of this conference. And thank you all. And I am open to questions. I also forwarded the quiz of this session to the organizers, and I think organizers will distribute it to the participants for the quiz. That means I'm open to the questions also now.
Thank you, sir, for the lovely walkthrough that you get. So the set of questions that are here is, this question is by Devmallo and Otoshi Lahiri. Both of them have the same question, that in deep learning, there is a hyperparameter named epochs in fit function to control the number of forward and backward propagation. But in machine learning, how to fix number of epochs on machine learning models? Okay,
so that's a good question. So normally we start with there's also something called batch normalization technique also being adopted in the deep learning. But if we just forget this batch normalization, so we have the concept of epoch also in this machine learning. So we need to so that means what it does in each epoch, it tries to that means so epoch means a full data, right? A full flow of the data. So the way we can do something called a batch process. So instead of a mini batch, so instead of, or we can do a stochastic way. So instead of the entire data set, we can go with a mini batch technique where we try to take some of the data and we try to train the network. There is no particular thumb rule. I cannot tell that there is a particular thumb rule how we set the values. But normally we start with a low count of the mean batch, and we try to estimate the error function, and provided it is doing good, we can go on the other side of it. Either we increase it or we decrease it. Okay, that's the way. There is no particular thumb rule we can tell that you can do it like that.
So next question is from Srijani Dotto. She's asked that, can CNN work with text?
Okay, so CNN work with text. This is a very narrow area. Normally in the text we try to do with RNN, right? In the RNN, recurrent neural network maintains a history of the previous outcome, right? Now if we can generate a sort of feature space through RNN, and then what is done in the case of there are some applications like image annotation, right? Image annotation or giving a story to the image. So what is done in those type of applications? First of all, CNN, we don't use the classifier of the CNN, but what we try to do, we try to extract the features from the CNN. And then the features are being fed in an RNN to represent a sequence of features. So a sequence of features actually defines an object or a scene. That means if I have a sea and if I have a person, I can tell that this is a seashore where a person is. So this type of image captioning attempts have been made where they have integrated the CNN and RNN together. But only for text, the use of CNN is pretty scarce. I don't think much is there. Yeah.
So the next question is from Paul. He's asking that if the number of hidden layers are much higher, then the final output is more efficient or not, whether this statement is true or not. Like the number of hidden layers.
Okay. This is not always needed. It again requires your understanding. So the hidden layers try to generate some that means it tries to operate on your data and combine your data in a more that means in multiple number of times if you have more number of hidden layers. So now the hidden layers are only required when you require multiple transformations from your data where you emerge and the point you have to take a decision, right? And this number of transformations you require on the data defines your hidden layer what you need to feed, right? And that is not always true that a number of hidden layers more is better because many of the times we have seen that for the practical problem. Suppose we are working with a problem where we are trying to define a robotic vision which will try to analyze the actions of the customers in a particular store area. So if you look into the standard networks, they have a large number of that means they have class outcomes of around 100. Right? If those is the class outcome, you require a large number of layers to generate the predictions. But in the case of a departmental store activity, there are only some 10 or 12 actions a particular customer can do, which are useful for me. In those type of things, we need to reduce the number of nodes in that number of layers because the classifiers need to have work on so number of class levels. So it depends on the exact need, but always reduction in the number of layers reduces the cost of your network in terms of your training and also resource requirement in the runtime.
Okay, so the last question: what is any practical application of leaky ReLU? That is a question asked by Professor Partha Ghosh.
Okay, that's a good question. So leaky ReLU, as I told that means it if you are doing a ReLU, it just squashes the outcome to zero, right? And you cannot and in the case of a vanishing gradient. A gradient problem you cannot you cannot actually take a particular use case directly like that. But what I can tell you have to understand this in terms of a vanishing gradient. So what is this gradient descent tries to do? Gradient descent tries to evaluate the influences of weights, okay, on your error, right? And you do a back propagation of this, right? And this back propagation tells that what is the effect of the weight in the error. So which means that whether the weight should be increased or decreased to have a lowering the error. Now what happens is that in the case of vanishing gradient, your ReLU function has squashed that outcome to zero, which means that you don't observe that means obviously zero after a certain point of input. So it doesn't observe any change in weight. That means no influence is there on your outcome, right? And that doesn't settles the weight. And if it is the midway of your network, you cannot further progress in the backward path. So if you have to do this in a backward path very efficiently, and you have to go to the first layer of your network from the last layer of your network using a back propagation strategy, you can use the leaky ReLU because leaky ReLU still differentiates between the outcomes, though the outcomes are negative.
Thank you, sir, once again. So this concludes our session 1. The quiz sir talked about, I will share the link in the YouTube chat as well as the Google Meet chat. Please fill it up and we will meet again at 2:15 p.m. Thank you, sir, once again.
Thank you all, and thanks to the organizer, thanks to the participants, and I hope that you have enjoyed my lecture. A lot of things I have tried to discuss. I hope that some of the things you have acquired with this, and I expect that you can connect with me, you can connect with your research, and I welcome all of you to my research. Thank you. Thank you all.
Thank you, sir.
Thank you. Thank you.
So this concludes session 1. We will meet again at 2:15 p.m. Thank you, everybody. Welcome everybody to the second session on day 1 of 2-day webinar on future generation computing and applications. This is the first part of the second session. This is on influence control in social network, graph theoretic aspect by Paramita De. Paramita De is a faculty in the Department of Information Technology, Government College of Engineering and Ceramic Technology, Kolkata. Her research interests include social network analysis, distributed computing and data science. She has authored 16 research papers in international conference proceedings and reputed journals, of which 2 of them have an I-10 index. She also acts as reviewer in IEEE and Elsevier. Please, Paramita De, please come to the talk and you are invited.
Good afternoon, everybody. Thank you, Kinshuk, for your nice introduction. প্লিজ শেয়ার হচ্ছে না, একটু দেখ না বৃষ্টি, স্ক্রিন শেয়ার হচ্ছে না, জানি না না ল্যাপটপ থেকে শেয়ার হচ্ছে না, কিছুতে শেয়ার হচ্ছে না।
Please have some patience. There is some issue with the uploading of the PPT. So please have some patience and we'll resume our conference in due time.
Share option plus single. Screen আছে ওকে।
There has been some technical difficulties, so please hold on and we'll resume in 2-3 minutes time.
Networks are powerful communication tools reaching hundreds of thousands of users. To understand how threats go viral and what role influencers have in Communications 2.0, the European Parliament's European Science Media Hub has brought together a panel of experts to debate the issue.
It's very important today to understand how virality works. It's really important to understand how this new social media can influence people or even manipulate messaging.
It's not an exact science how to make social media content viral. If it was, then all the big brands would be doing that. All the advertising would be viral online. We always know in retrospect what did turn out to be viral and try to draw conclusions from that. Of course, there are many variables playing into that, from the algorithms that the platforms apply to the content of the viral through human behavior.
So how do we get our messages through effectively on social media?
At my agency, we use principles that we call resist principles to get people to share content online and to get traction online. The Z stands for zeitgeist. We tap into what people are talking about already online. The E stands for emotion. We try and trigger people's emotions. The U stands for
make sense of it all. So if you have
Many of the viewers in the previous session were asking for the quiz link. So the quiz link has already been shared to your mail, and a link has already been added to the YouTube chat. So please look at the YouTube chat and you will find the quiz link. And a mail version of the quiz link has also been sent. So if you can answer the quiz link from the chat or the mail, both of them can be answered. So do whichever pleases you. And please bear with us a little bit because there has been an issue with the uploading of the PPT. Once it is resolved, we will begin our lecture. Thank you for your patience.
হ্যালো কিংসুক,
হ্যাঁ বলুন স্যার।
বলছি এটা কি হচ্ছে, প্রবলেম কোথায় হচ্ছে?
এই ইস্যু উইথ শেয়ারিং, ওই পিপিটিটা শেয়ার করতে অসুবিধা হচ্ছে।
ও
Who is the speaker now? Kingshuk? Hello, Kingshuk.
Hello. Yes, madam.
Who is the speaker now?
The speaker now is Paramita Dey. So she's trying to upload the PPT. So there has been a technical issue with that. So that is why we are waiting for some time. And I think it will be resolved in the next 3 to 4 minutes time.
Obviously. Okay, thank you.
হচ্ছে না তো প্রেজেন্টিং টু এভরিওয়ান তারপরে তো কিছু দেখাচ্ছে না
Yes, the PPT is somewhat visible now.
actually it is visible from the mobile.
Okay, that's not an issue. It's visible, so we can continue.
Okay, thank you. So, network data generally consists of two kinds of data or information. One is content and another one is the connectivity data. Content data is mentioned, it is in a slide where it is a viral content that is like when this data is viral through the network due to the content of the data. And another one is the connectivity, that is how this node is connected to the other network. Now for the content of the data, we cannot make sure that which kind of information will have more importance. Like, you know, in last week, there was some people who sitting in front of his computer and doing nothing for 2 hours, and it becomes viral. So if we want to make a viral data or information, so for the content, we have not such clue which contents of data will be more effective or more viral. So for the connectivity part, we can do some things, and it is about that we can exploit its graphical information through the network so that this data can reach to maximum number of people in the network. So this is a brief overview of my speech. It is started with the introduction about social network, what is social network and all about that, and how to analyze this social network data, which is a large amount of data in the using some paradigm, and how to do the influence control. Actually, what is influence and how we can control it using some influential nodes or links and maximize the influence or minimize the influence depending on the needs of requirement of our content or the utility. So maybe 20 years back, the information media, we are using the information media like billboards, radio, newspaper, or TV for the information propagation. But in present scenario, when there is a different social network present like Instagram, Facebook, Twitter, YouTube, Google+, we are using this kind of methods, and this is not in a broadcasting mode. That it is a two-way approach. If you send some information, you will get some feedback, and you will get some review of your information, that how it is useful or affect or influence other people. Now, how does social network look like? It looks like a graph, and it is extracted from one of my students' Facebook profile back in 2016 from his Facebook profile. Now it is banned. Actually, 2018 there was a scam of data leakage. Actually, Facebook data is private in nature. So there was a scam in 2018, and back then this data cannot be extracted. And from this, at that time, at 2016, it can be extracted using an open source software called NetBeat. And this was, it was in some crude data form, and it was analysis through software R, and it just looked like that. This small picture you can see, this is the profile picture of the Facebook profile that is attached to this particular student. Now, before coming to the social network analysis, I want to introduce about what is social network and what is online social network. Social network can be defined as a social structure of individuals if they have some connections or connectivity. Like if you form a social network group, then it can say that it is a social network. And online social network is analogous to that. In online social platforms where its social network is formed in based on some career interest, activities or background or some common interest, like you want to play video games, and those who are interested in playing video games can connect through social media and can form an online social network. And what is social network analysis? Social network analysis, it is a mapping and measuring technique that is in the social network data if you want to analysis or want to get some insight, because it produces huge amount of data. So it is obvious that if this data can be analyzed and can be used for some other purposes like some viral marketing or advertisement. So we have to find out or analyze the data which is already present or generated the social media people. So this social network analysis is this technique for that. Now, how does it look like? I have just shown it is in the previous figure. Here, all data are represented in the form of a graph, and all users are represented as nodes or vertices of that graph. And with this, for the edges, if there is a connectivity between two users, then there is an edge between them. And if the connectivity is more, then the weight of your edge will be more. And if the connectivity is less, then the edge will be, this connectivity, weight of the edge will be much less. And how to collect the data from the social network? Actually, there are different crawling softwares from where you can collect data. Mainly Twitter data can be collected very easily because it is public in nature, and it is generally found in JSON format or CSV file. And this data can be used also using some hashtag or from some user profile. Now this is also a figure in CSV format. When JSON data is collected in some software, it is converted to a tabular file. It is known as CSV, and you can see a partial view of the CSV file where this level, some level, and there are some characteristics are shown in this table. Now, these two figures are extracted from Facebook and Twitter respectively. The left-hand figure is extracted from Facebook, and it's a very basic structure. It is processed through a software called JP. And this basic structure, you can see it is just like a hairball or mesh-like structure. And here, we are not just getting very much information, but you can see that there are some dark and dark edges which indicate that there is more communication between these two nets, whereas for some smart nets, there's less communication, and there are some different nodes also where they are not communicating at all in this profile. And this right-hand side data is extracted from Twitter network from a single user. And the middle nodes denotes the ego node, which has a maximum connectivity. Actually, ego nodes is the influential nodes access have various connections in the network. So it is very important also in case of influence maximization or minimization problem. So for the next one, you can see this three initial graph it is three profile actually. These three profiles were extracted from Facebook, and from this hairball-like structure, you can see that from the left-hand side figure, leftmost figure, this has very less number of connectivity between the nodes, though the number of nodes in all three profiles are almost same. But you can see the third one has a very dense connectivity. So you can say that this particular user is very popular in Facebook, and he has very connectivity with the other people in his profile. And here is a small distribution part, that is a small analytics where we found the male-female distribution, and we find that for the first figure, there are three values, that's male, female, and null. Actually, the null genus who's the people who are not disclose their male or female identity actually. And for all three, these males are mostly as compared to the female, the male nodes are more in the this profile. It may be of the fact that it's not true, or maybe that incidentally all these three profile belongs to three male profiles. Now for the social network analysis, what's the problem faced with? What's the problem faced with also with any kind of big data? And social network is very high, dense population of data populated each time is in a very large volume. So the main problem is faced is like that all problems is faced in like big data paradigm. For example, the volume, the first one is a famous V, 4 V's. The first one is volume. Online social network has a large volume of data, and you can understand that with the increasing of this online social network data, this volume becomes more and more, and for processing of this kind of data, we need distributed framework for computation and mining. And the second one is variety. As data social network is not a very structured form or semi-structured form, so we can get text data, video data, image data, etc. So we require a database which can contain all kinds of data like this. And the velocity, as all social media contains time stamp along with it, and it is very transient in nature. For example, now at present scenario in COVID-19 situation, the data like mask, COVID-19 pandemic data are populated in a very large scale. But maybe after 20 years after, there will be no relevance of data actually. So this is a very transient kind of nature, and when we have to make the analytics, we have to mind that this data will be so much analyzed in the context of the time also. And the fourth one is the veracity. That is, it is qualitative data may be qualitative also. So all files are not available for all users. So we require NSQL database. NSQL now stands for it is no SQL, but not only SQL. So we use database like MongoDB for this purpose. Now for the modeling of social network, the main two properties we are dealt with that most of the real world network follow the rule of smaller phenomena. It is proposed by Strogatz, and it's about that path length and of the network will be very less, and the clustering coefficient will be very dense as compared to the random network if it is wired with same number of nodes. So as compared to the random network with same node degree distribution, we will get a less path length and high clustering coefficient value, so that the diameter is very less as compared to the node present in the network. And it is famously known, it is famously called as the famous 6 of notation, where it is stated that if you started with one user in social network and reach to some other who you actually don't know, but the distance between you and these people is maximum 6. Actually, they started with the Argus project. He was a mathematician, and he stated that if it is there is a network, if there is some collaborative work in mathematicians, then this length will be 1, and after a certain period of time, it will find that 2 mathematicians have the maximum distance of 6, although they never met. And for the present scenario, the small world network criteria is not always applicable for social network, and now it came the scale-free network. This is figure actually obtained from Wikipedia, which shows the scale-free network where node degree distribution follows the rule of power law. That is, it is logarithmically or exponentially related to the number of nodes present in the network, and this average length is much more than 6, and it is in the range of maybe 12 to 14. But if you can minutely see that, you can find that a large scale-free network also is a collection of small world networks. That is, we can say that scale-free network is a collection of different small world network, and so the small world property we can use in a elaborative way to represent the scale-free network also. Now, how to influence this? How to influence, maximize or minimize your influence or control your influence through social network. Now, what is influence? It is a law. It is a general definition. That is, if you have a power to change the opinion of others, then you can say that you have influence to this particular person. So, in online social network, we measure this simply by the number of levels you have reached or the number of people that you have reached through your communication is the influence of the particular user. Now, to measure how to control the influence in online social network, we first try to identify the influential nodes or links in the network. After identifying influential links or nodes, we'll use that for the influence maximization or minimization problem. For getting the information about which node will be influential, we use a measure called centrality, network centrality property. And before going to that, I want to share nodes or user classification method in social network. It's broadly, there are different models actually. The first one is the Dilley-Kendall model, where there are 3 kinds of user: ignorant, spreader, and stifler. Spreader are the nodes who are generating the information and propagating the information in the social media. Whereas ignorants are the nodes who have no idea that this information is propagated, so they did not get the information, and as they have no information about this particular information, so they are not participating in the communication. But the Stifler node, the third one, Stifler nodes, these nodes are the property that they have the information from the network. They know that this information is circulated, but they are not interested to circulate it in the media. And the second one is the behavioral model. Both ignorant and Stifler nodes can be identified as dormant node in behavioral model, and the spreaders can be said that it is an active node in the network. And the third one is the flow model, whereas there is source and sink and participatory. Source are the nodes who are generating the information, sink are the nodes who are getting the information, and participatory nodes are those nodes who are helping the information flow from source to sink. It's coming about the centrality measures. I just inform you that for influential node selection or identify the influential node, we use the property of centrality measures. Basically, this property is generated mainly for the nodes which are present in the small world network, but if we can utilize them in large scale network also, using in an efficient way. So there is some application of centrality measures. It is not only used in social network only. It can use in other network like biological network or network breaking problem or any other type problems also. But in social network, it is used to identify the influential nodes. And here are some figures which depict that which nodes will be have some high centrality measures. You can see that this node in the right-hand node side, it has the highest node degree connection. That is, it is connected with the highest number of links in the network. Highest between the centrality and closeness centrality, all of is based on shortest path. And in network, we are very conversant with the terms as shortest path. That is, if there are two nodes, the minimum hop using minimum hop. If we want to reach from this source node to sink node, then this path will be termed as shortest path. And another one is the pageless centrality and the eigenvector centrality. And just briefly discuss about them. The first one is degree centrality. As we just mentioned, it is the node which have the maximum node degree value. And you can say like Amitabh Bachchan or Narendra Modi have many connectivity in the network, so they have a very high degree centrality. It is not always true that degree centrality has the highest number of influence maximization. The second one is between the centrality I just mentioned. It is dependent on the shortest path. It is defined as the node which has the maximum occurrence in the shortest path. If we consider all shortest path, then the nodes which have maximum occurrence, this node has the maximum highest between the centrality. And the closeness centrality is the node which have the minimum distance with all other nodes. So if we denote as the distance metric, it is the inversely proportional to the distance matrix, and which have the minimum distance, it will have the highest closest centrality value. Eigenvector centrality, that is, if we consider eigenvalue, if we calculate eigenvalue for all nodes present in the network, then this value is defined as the eigenvector centrality. And the another two nodes are PageRank. PageRank is famous Larry Page of Google. This proposed this algorithm of PageRank. It is actually used for the finding the Google page when you try to find a link in the network in Google. Then PageRank is not only how these nodes are connected to the other nodes, but it denotes the weightage of this node. But that is, if you are connected to some important link, then your PageRank centrality will be higher, rather than if you are connected to a person who has the less importance in the network, then your page rank will be reduced. And then there is another one is K core. It is the maximum subgraph actually you are finding. That is, if we are defining a predefined value K, and if some value, some centrality, no degree value is less than K, then it will be eliminated from the network, and from this we will derive the value of K core centrality. Now, about the inference maximization problem, that is, if we derive this centrality measured value as influential node, then how to use it in inference maximization. In inference maximization is a mechanism so that the information can flow using minimum cost. That is, we have to use minimum number of source, and using that we want to reach maximum number of people in the network. And we can use the centrality nodes as propagator and source node of the information propagation for this centrality value. And here is a small pictorial overflow of this inference maximization. First, we'll get the initial network extracted from the Twitter or any open social network site. After that, you will classify the node, as I just mentioned, as source, propagator, ignorant, etc. And after the classification, we'll identify the influential node, and using some propagation methodology, we'll try to find that to how many nodes it reaches. So here is a figure just published in one of my paper where we are using, it is a Bitcoin network. In Bitcoin network, we are using different centrality measures value. When you choose a random node for the seed node or source node of the propagation, we can see that we can reach only 600 people in the network. Whereas we are using eigenvector centrality, we reach to the maximum 1500 people, which is almost 2.5 times of the network. And we can see we are using just BFS. This is for BFS propagation. That's search. We can use other propagation method also for the simulation purpose. And we can see here that this degree centrality value only reached to the 1,000 people. So it is not like that they are connected to the most number of people. So it is not like that they have the maximum capacity to influence other people. And what is the drawback of that this particular problem is that it has a high computational and storage complexity, because the number of nodes is very large in the social network, and the computational complexity in the order of n squared in case of eigenvector and in order of n cube in case of between centrality. So you can understand this computation is not so, it requires a large storage space, it requires a large computational space. So we have to solve the problem, because to convert this network to getting the information from the network about the centrality value, if it is too complex, then we have to find a methodology for that. For solution of this problem, we can use two kinds of paradigm. One is degenerative network, which is a representative network of the original network. That is, we are not using all nodes and use only the nodes which is very important in the network, and we are reducing the other nodes, but the basic properties like node degree centrality or clustering coefficients are not changed for this using this degenerative network. And we can use the distributed framework also, like Hadoop and Spark. And here is a diagram For the previous figure, it is the same that I am using. And minimize using I don't want to tell you the same. It's not the same one.
Hello, I think there is some audio disturbance. So if you can just hold on some second and then restart maybe, because some audio disturbances are coming.
Hello?
Yeah, it's audible.
It's audible now?
But there is an electronic disturbance that is coming up. So maybe move out from any computer or some stuff, because there is an electronic disturbance that is causing the disruption in sound. Yeah, you are audible, but there is a constant disturbance that is coming, actually. It's a background noise that is coming, actually.
Hello?
Yeah, there is a laptop or a mobile which is near you, which is impacting your speech, actually, the voice. So if you can move away from a laptop or something, I think it's a magnetic feedback or something like that.
Okay, so actually that is the laptop. Actually, it is raining now.
Okay. So
It's fine now.
no, there's still a disturbance, actually. The voice is not clear. It's breaking up.
Okay.
Maybe you can move out and then come in again. Maybe do something like that.
Is it fine now?
Yeah, it's still breaking up, actually. Yeah,
Hello?
yeah, maybe you can try to get out of the meet and then come back again. That should be a better option, I think. So there has again been a disruption due to voice. So we're trying to correct it, and we'll solve it in a few minutes. Please have some patience. Yeah, we see in the comments that distorted sound is coming. We are trying to deal with it, and we'll be back in a few moments' time. So there is essentially a network disturbance, actually. So please have patience. We'll resume in a few moments' time. This lecture is followed by a very interesting practical session on this theory only. So you will get a hands-on experience of whatever is being talked here. So we'll go by this lecture. So please hold on, and we will resume it as fast as we can. So I guess we'll resume it in a few moments. So we are back. The speaker has already shared his presentation and will resume in a few moments' time. Thank you for your patience.
And now, after K-code generation, we can see that this is almost, we find the same type of thing. And the second process we can use like map reduce paradigm. We can always know this. It is from Hadoop architecture, where you are using map and reduce, breaking all the systems using mapper, and after that we are combining all the results in reduce paradigm. And we can use Spark also, where map and reduce are combined. And the second one is the inference minimization problem. Inference minimization, we required it when we want to minimize the inference because of the fact that it is harmful to the society, like rumor control. In that process, we can use removing or block the centrality nodes. We can remove or block important links. We can do some anti-campaigning. That is, if there is some misinformation, we can use some anti-information which is campaigning about the misinformation, and use the same influence maximization methodology for influence minimization of this particular rumor. And also you can use the community structure, and you can use or delete the link which is a breach to the different communities, so that it becomes more efficient for the influence minimization. Here's a small case study where we are deleting some important links and as well as important nodes, and try to find out that which kind of which will be more efficient in influence minimization problem. And for blocking some important edges, we are using the methodology of edge betweenness. Edge betweenness is the edges which have the maximum occurrence in the shortest path. That if we want to reach a node from one node to another through shortest path, if we break the link between them, important link between them, and then it is obvious that this influence will reach to the minimum number of people in the network. So using this methodology, we're doing the influence minimization problem, and here is some diagram. So we can say the flow diagram, that is our selection of seed node, and we are blocking this, and after that we are trying to find out that after propagation will it work effectively or not. And we find that the before blocking, we can see it is reached to the 50 number of nodes, but after blocking some important nodes, we will find that this blue color, which has the highest influence minimization in terms that it is to the only to the maximum 22 number of peoples as compared to the 50 peoples originally. So it is we getting after blocking the edges with highest edge between it. So this all four figures, we are just using different source node part and source node, and we find that for every figure that the nodes with when we are doing we're blocking some influential edges, it has the maximum influence minimization we can see observed in the graph. So now we are trying research idea that instead of using some influential node, if we use some influential link, then this influential minimization problem will be much more better, and to identify this influential link will be crucial. And that's the end of my lecture. And I think it's very disturbed due to some, at first it's some network problem, and after that it is raining over here. So I beg your pardon, all the audience. And it's some bibliography, some papers which were published in this area, information maximization and minimization problem. And here are some particular papers are the classic papers of social network. And if you want to implement the social network, there is the bibliography of the, it is all open source software, so you can download it and work of your own, and you have not to pay. So thank you.
Thank you, Paramita Dev, for this interesting lecture. Although there has been disruptions, but the lecture as a whole was very good. Now, I invite Agneet Chatterjee, who has done his BTech from Jadavpur University, and he's currently Associate Software Engineer SalesForce, to throw some light on the implementation aspect of the previous talk. So, Agneet, if you can share your screen and share us your views.
Sure. Thank you, Kingshuk. I'm going to start sharing my screen right now. Yeah, I hope all of you can see my screen. So
it's coming up. It's visible.
All right, thank you. Good afternoon, everyone. I am Agneet. I graduated last year from Jadavpur University, Computer Science Department, and right now I'm working as a software engineer in SalesForce. Today, we'll talk about the implementation aspects of the lecture that Paramita just gave on the graph theoretic aspects and the social networks. We'll talk about the challenges, a few implementation techniques, a few tools that make our life easy when we want to implement what we've thought about the research hypothesis. So a quick overview of what we'll talk about. We'll firstly cover data collection, data which is the source of truth. As a researcher, we have multiple hypotheses, but we can only validate them when we have the right data, and our analysis on it validates what we thought about as a research hypothesis. Then we'll talk about pre-processing the data. Our data is not just enough. Pre-processing is a very core part of data collection, because it ensures quality and it ensures that our only focus is on our hypothesis and not the data quality. Then we'll talk about the implementation aspects of it, where we'll talk about quantifying what we've thought about. We'll talk about a few techniques. We'll talk about a few data structures and their advantages. And finally, in the 21st century, we'll talk about the visualization, because with the advent of data and science, there has been so much of data that's available. So it's very important for us to explore what we see, because seeing is believing at the end of the day. So a very quick introduction, and the Paramita has covered majority of it. So what are graphs? Graphs can be something that can be as simple as a project plan, or something as humongous as a big web page, something like a Google indexing. Diodes are called the building blocks of social networks. For example, alpha knows beta for 4 years. Then in this case, alpha and beta are going to be my nodes, and the relationship is their edge. And the 4 years, which quantifies the relationship, is the weight of the particular edge. So what is social network analysis? If alpha and beta share a relationship for a certain years, then they are not aware of the big picture. This has a butterfly effect into a large space. The relationship between alpha and beta impacts something else or someone else that they are unaware of. And that is where social network analysis comes into the picture. It helps us extract layered impacts which go through multiple layers and multiple edges. Quick applications. Social networking is used in community detections. It's used in recommendation systems where different organizations like Amazon suggest products based on what we've bought before. And of course, we can do epidemic spread modeling with the use of social networking. Now, coming to the first aspect of today's lecture, we'll talk about data collection. As I previously mentioned, data collection is probably the most integral part of any research work. Snowball sampling is one such technique. Now, what is snowball sampling? It is a general notion that people who are of the same kind usually talk to or interact to other people. And this nature is something that snowball also behaves like. That is the concept of snowball sampling, where people of the same kind interact with the same kind and give you a snowball-like behavior. Social network analysis usually considers data which are relational in nature. And what does that mean? It depicts connections between individuals and groups. They can be social data, they can be co-occurrence data, or they can be distance data, where it's simply a distance between place A and place B. The data types can be binary, they can be categorical. And what do we mean by categorical? Categorical is the extent of a relationship. How much do you like someone? How much do you hate someone? So a scale, categorical is something that we can define by a scale. And then there are intervals, which are basically numbers and quantities. What are the challenges? When the 21st century started, volume of data was never a challenge because we were looking for data. And now in the 21st century, we have so much of data that we have to scratch our heads to see how and what is the best way of optimizing it. That is probably one of the biggest challenges. And another big challenge that we see today is something called code mixing, where people interact with each other, not just in one language. They talk to them in multiple languages, English, Hindi, Twitter, everywhere you would see not one languages, but multiple languages. Getting those languages, separating their emotions out, and then following the trends and social patterns is one big challenge that we are seeing right now. The classification is what we'll cover in the next slide. Firstly, we'll talk about data repositories. Now, what are data repositories? These are open source and publicly available data sets, which are free to be used by any researcher or any student who has an interest in social network analysis. What is the advantage of this? They are multi-domained. There are citation data where an author A and an author B, how many papers have they collaborated on? What is their common interest? All of that data is captured. There is signed data, which is basically positive or negative data. Then there's product co-purchase, as I previously mentioned. Companies want to sell product A with product B. All of these networks are available online, and all you have to do is just go to the internet and download them. The networks are also of different types. We have scale-free network, we have small world network, and one important network you also have is egocentric, where egocentric network is one of those networks where the network is centered around one's individual's connections, and that way we can cluster our entire network around one entity. They're of varying magnitude, and most importantly, these are all real-world data. So our hypothesis can be validated on real-world data. I just gave in quick sources here. One of the biggest repositories of network data is the Stanford Large Network Dataset Collection, also known as SNAP. It is compatible with C++ and Python. There are APIs available, and it is scalable with optimal graph representation. We also have something called a social computing data repository, which have APIs. So you don't have to download anything online. You just have to fetch the APIs and consume them to receive the acquired data. What are the advantages? Number one, as a researcher, we always look out for comparisons. We always want to see what has the other author done. The good part about all of this is that because this is publicly available data, these data sets are widely reused. So comparisons and implementations are very, very easily available. One of the disadvantages is that the same data set is uploaded in multiple resources. So you will see multiple versions, multiple data types. That becomes a bit of a challenge when you're trying to figure out what is the right and original data. Next, we'll talk about data crawling. In case you want most up-to-date data, in case you're not satisfied with the data that is there in the repositories, we have something called a data crawler, which is basically mining of information and data from the World Wide Web. It gives you the power of customization. And when I say power of customization, it means you can crawl anything and everything with the right access. You can validate your hypothesis on a diversified collection. And crawling is not just for data set collection. It is used by companies like Google for search engine optimization and web page indexing. A couple of sources here as well. Multiple companies like Twitter, like Facebook, have consumable APIs which organizations can use to expose their data, and we as consumers can fetch the data as and when we need. We have the Graph API of Facebook, which is of late garnering a lot of attention. We have crawlers as well. Now, what are crawlers? Crawlers are basically small bugs or small tweaks that you let go on a web page, and then they will give you the data that you're looking for, the amount of data that you're looking for, and in the format that you're looking for. The good part about these are open source, and they can be used in any platform. They can be used on Windows, Linux, or Mac. And their implementation is very easily accessible. They're implemented in Python, C++, and Java, just to name a few. What are the advantages? One of the biggest advantages, as I see it, is that you're contributing a new data set. Something that you have crawled can now be contributed to the research forum as a new data set, and people will appreciate, and you will garner the right amount of respect. Disadvantages, there are a few. For example, there are rate limiting SLAs. What do I mean by that? When you're trying to consume the Twitter API, you can only make 15 calls per 15 minutes. As a result of which, this is very time consuming, and you will always have to be on your toes, making this a very performance intensive measure as well. Next is something that the research community is looking at of late very, very heavily, and that's synthetic data modeling. What is synthetic data modeling? It is basically data sets that are created, which are not real in nature. They're not based on real life factors, but their importance is, as we are the creators and owners of this data, we can tune their statistical patterns, we can tune their skewness. And this data can be heavily used to garner proof of concepts, because this is fresh data, it does not have any outliers, and henceforth, this is a very idealistic data set that we can work on. And probably the most important factor as well, this kind of data respects privacy. Every data set that we garner from the internet has to be anonymized, Facebook data or Twitter data. But as this is a synthetic data, right? This does not have to respect privacy, because all of this is fake data. So you can skip the pre-processing step of anonymizing all the data that you get. A few sources again, GraphGen, which is based on IBM's quest of synthetic data generation, and Facebook's Graph Benchmark, which is tuned to simulate multiple workloads, where you can simulate a graph's workloads on multiple parameters, low, medium, or high. One of the biggest advantages is you can replicate multiple simulations which have not yet happened yet. For example, in this COVID situation, we can create mocked-up data to see what is going to be the impact in the next 6 months. The real data is not applicable, but we can look into a possible future with mocked-up data. Disadvantages, of course, it takes a lot of time and effort, and sometimes it misses important outliers. Outliers are also very important to data, but as this is synthetic data, this is going to be unrealistic data, and as a result of which, it will be missing a few outliers. Next, we'll talk about data preprocessing. Now that we've gotten our data from wherever source we are most comfortable with, we'll have to fine-tune the data. There is no research work where there is no pre-processing involved, because raw data is hardly ever consumable. It consists of spam and noises, which are garnered due to malicious and automated users. It consists of inconsistencies, and it consists of incompleteness. A link between A and B might be missing, or a link between some other entities might be missing. And most importantly, some of these data do not have the right access, as a result of which we have to perform data preprocessing. Data preprocessing is one of the factors which depends on the domain of our research. We can preprocess this as and when how we like it. What is the utility? The biggest utility is that we have to focus on the validation, and if we do data preprocessing, we don't have to worry about the data quality. It removes redundant outliers, and it gives you unbiased data. The biggest advantage today is that there are multiple tools that support us. These tools enable one thing. You can focus on your idea and let the implementation be done by these tools. I'll talk about two techniques of data preprocessing here. One is data reduction and one is data conversion. So what is data reduction? We get multitudes of data from the World Wide Web. It's a huge World Wide Web, right? So we want to sample our data, and we want to get a representative sample, which is smaller in nature, and derive a static snapshot. And how do we do that? There are three widely used techniques. One is a random node selection. In random node selection, randomly a few nodes are selected from the real huge graph, and they're selected on a certain basis. Maybe there's a threshold of selecting a few nodes which have a high node degree. But the problem with this is that only a few high node degrees will be in our representative network. which will not be a right measure of our real graph. The next is random edge selection, where we want to select random edges. But again, this suffers from a small problem. What our representative graph will be a very sparse network, which will again not be a representative of a huge real graph. Lastly, we have something called a random exploration, where we perform multiple iterations, like a depth-first search or a breadth-first search or random walks to get not just nodes or edges, but to get them as a single unit so that the cohesiveness is maintained. Another thing that we do is something called a stop word remover. Now, in everyday language, in everyday social media, we use words which hold no importance, like pronouns or simple terms, but we want to focus on the influential words which gives us opinions, which gives us factors, like adjectives, or like a strong opinion or a hate opinion, whatever we want to research on. Similarly, we also perform data compression, which enables us to do efficient neighborhood queries. Followed by that, we have data conversion. Again, one of the biggest parameters of any data set generation is privacy. It is as our researcher's duty to remove sensitive information so that anyone's personal information is not available as a public data set. But we also have to ensure that we balance that with the utility that the data has. Secondly, I want to talk about cosine similarity. For example, I have two people, alpha and beta. And alpha has an opinion A and beta has an opinion B. So the similarity score between A and B is given by a very simple metric, which is called the cosine similarity. And the graph, which is the edge between alpha and beta, the edge weight of that would be the similarity of their opinions. So if you're trying to build a network where we want to get an opinion about two things, we can simply go ahead and perform a cosine similarity to see what are their opinions, how different their opinions are on this particular matter. And as we talked about before, dyad. Each such an edge is a dyad which adds to the entire network. Now we'll go into the implementation. Now, social network analysis is one of such fields where implementation knows no bounds. Here, I only wanted to touch base on a few things that are very easily accessible, and I also want to talk about a few data structures. Number one, community detection. Now, what is community detection? It is simply finding groups in a complex network through a graph representation. Birds of the same feather flock together, right? Similarly, this structure is how we represent it in a graph. On a very broad aspect, they can be classified into two ways, agglomerative and divisive. Now, what is agglomerative? It means that we start with simple nodes and edges, and then we cluster them into communities until we reach a specific threshold. And divisive is where we start with an entire graph and then divide it into sub-communities to see what is the best possible solution. Griven-Newman is one of those algorithms of divisive natures where we do iterative removal of edges which have the highest edge between its centrality. And walk track is one of those algorithms which is based on the random walk. And it's simply based on the concept that if you take short random walks, you would ideally be in the same network. The best part about all of this is that these are just a function calls in Python and R. A simple function call of cluster walk track for a given graph will give you the entire community. Simple, isn't it? We just have to think about what you want to use, and there are already millions of implementations available. Similarly, second concept I want to talk about is influence spread. One of the very famously used influence spread models is the random walk model, which is a Markov process. In simple terms, what does a Markov process mean? It means that the future and the present does not depend on the past. The advantage of random walk that unlike other algorithms, it does not come to a dead end very often because of its randomness. The second model is something that we should all be relating to in real life right now, is the SIR model, which computes the theoretical number of people infected with a contagious illness over a period of time. And now I want to quickly talk about one of the best packages out there for social network analysis, which is NetworkX. Python provides this functionality and it lets you create, manipulate, and ask for it. It will have all its implementations. You can import data as you need. You can do any sort of centrality, right, from eigenvector or closed-link. You can do community detection. You can do k-cliques or bipartitions. You can do traversals and small word algorithms. This is one of the most comprehensive packages available online, and it is very optimized in nature as well. Next, I want to quickly talk about the data structures that we use while doing social network analysis. Number one, we'll talk about adjacency matrix. Now, what are adjacency matrix? They're simple two-dimensional array where rows and columns are both consisting of nodes and the entries are the edges that they represent. What are the advantages? It is fairly easy to understand and provides a very fast random access to any cell in the matrix. And it is also the basis of the very famous UCI net software analysis. Disadvantage, it is not scalable. The data storage requirements are proportional to n squared, where n is a number of nodes in the graph. And then comes sparse matrices. Sparse matrices are applicable when most of the elements in the graph are zero. And what do we mean by zero? Where it means that the entire graph is sparse in nature, where there are less connections, which is synonymous of our social network analysis. They support efficient modification and they also support efficient access. What are their advantages? It saves a significant amount of memory and speed, and it saves a lot of unnecessary low-level arithmetics. For example, in a sparse matrix, we already know that the number of zeros are less. So we can let go of any computations which multiplies, divides, or additions by a zero. The only disadvantage is that they're less informative because of their sparse nature. And next, I want to talk about visualization, which is probably one of the most important factors in the 21st century. With visualizations, we can generate learning situations and insights. We can vary the size and color of nodes and edges to modulate and depict what they represent. Community detection as a whole can give us lots of metrics, but until we see how the community looks like, are we really going to be pleased with how our algorithm works? The only challenge here is that our current modern system, pixels, do not support the density, do not support the entire fragile nature of how the networks look like. And how easy it is to implement. Here's just a 3-line of code, and here's my graph. So, as I previously mentioned, in today's 21st century, the tool does all the things. All we have to do is feed it the right data. Next, I want to talk about a few packages which are very good in visualization. Number one, we have Cytoscape. Cytoscape is one of those tools which is ergonomic in nature. What does that mean? That we have to write no code to get any sort of visualization. What that means is that you just input the data, tune some parameters, and there you'll get the graph that you desire. Jeffy is another such link analysis visualization, which is readily available with metrics and loaded with insights. And finally, if you want to code, then we have R, which is highly customizable, and all the R packages support graph generation. So it lets you focus on ideas and not on implementation. These are all the references that I took for this presentation. You can go here and visit at any point of time. Thank you.
Thank you, Agneet, for this practical viewpoint. Now, to further extend this practical viewpoint, I would like to invite Swarnesha Chatterjee, MTech from GCECT IT department, to please present her talk.
Thank you, sir. Thank you, Mr. Agneet Chatterjee. Now I will be discussing. So let me just upload the PPT here. Is it visible? Is it visible?
Yes, it's visible now.
Yeah, thank you. So as my mentor already mentioned about the social media platform and what you can do with the data, so I will be describing how you can actually extract a data from a Twitter platform with the help of your Twitter API. So these will be the things that I will be discussing one by one. Now coming to what you need, the basic thing for starting of this kind of project. So first you need a real basic Twitter account, Python, and the main package for doing this kind of Twitter related data is basically Tweepy. So you need to install this package. So open the terminal and you can do this pip install Tweepy, and Tweepy package will be installed in your machine. Now when you have your normal Twitter account, to work with this kind of project, we need to change that normal Twitter account into a developer Twitter account. So what we need to do for that is basically we need to get here, which is apps.twitter.com, and it will take you to a page like this. So if you are new to it, it will be a blank page, but as I already have my app, so it will be showing my apps detail. But at the top you can see that it's showing create an app. So you can simply click here and it will take you to a page like this kind of a form. So you need to fill this form very carefully, as they will be like checking this form for a few days, because they are allowing you to connect with the platform and extracting data from that and manipulating data. So it's kind of a security matter. So for app name, you can simply give your project name and the website details, and it will ask you the organization details. So if you are a student, you can simply give your college name and college website. So the meaning in this form is this part, which is the basic description of your project. So before starting filling this form, what you need to do is you have a clear idea about your project, what you want to do with this kind of account and what you want to do with this kind of data. So when you have a clear idea, you can give a brief detail. You can give like up to 3,000 number of characters. So give a brief detail about it, and when you will do the create button, it will they will say that they will get back to you within like 3 to even 1 week. So within 3 days or 1 week, they will be checking this part mainly, like your program detail, project detail, and if they find it's completely secure, so then they will grant you. So when they will grant you, they will send you a mail like say your account is created. So for that, when again you will log in, you will at this kind of page. So there is the apps detail, basically your ID, name, and then the main thing from this developer Twitter account, what we want to extract is basically these keys and token. So when you will click this field, you will get these keys and tokens. So as they are completely unique to everyone, I am not showing the proper page, but you will get these 4 keys. So you will get the access token secret, consumer key, and consumer secret. So when you will have them, you can completely copy paste them and create credential file. Later you can import that, or you can simply copy paste them in your code. So now jumping to the first step of what you are doing or you need to do for the basic data extraction thing. So as I already mentioned that the basic package will be Tweepy, and along with that we have the cursor, stream listener, auth handler, text blob and all. So they have their one by one properties. So cursor is basically will help you to do with the pagination, basically extracting the home timeline tweets or homepage tweets, friend list for someone. Stream listener basically listen to the tweets. So it will when you want to extract tweets based on few keywords and hashtags, so it will help with that. Auth, as the name suggests, is basically help you to the authentication stream for live streaming the tweets. Now coming to the data manipulation part. So for the first thing you can do after extracting data is sentiment analysis. So for that we have this text blob, and we have the regular libraries like NumPy, Panda, and R for regular expression, because you want to give a clean tweet to your function before doing the sentiment analysis thing, because if your tweet contain a lot of symbols, so it might create a problem. So for that, now what we'll do is we will create small classes, small function in that to do a step-by-step process for extracting one by one data. So the first class is here, which is the Twitter client, and the main like reserved one in it, which is basically the constructor. So we are in the authentication part here with the help of like auth handler. Now we have the main thing that we are doing is extracting the user time page tweets, extracting the friend list, and extracting the home timeline tweets. So for that we have 3 functions, and the num tweets and num friends basically will suggest the number of friends or number of tweets you want to extract. So first we have created a blank list, say friend list. So cursor is basically a class related to the Tweetp module. It's basically with the help of the dot items, it's basically a cursor object. Like for every iteration, it will extract one tweet and will append it or say store it in this list called tweets. The same process is follows for friend list extraction and home timeline extraction. The only change will be here is for user timeline tweets, you are using this dot user timeline, but for friends you will be using this dot friend, and for home timeline you will be using dot home timeline. Now coming to the authentication part. So for that we have another class and say another function, and auth is basically the object. So with the help of auth handler, what you will do is you will be copy those keys and simply paste them here. So without manipulating even a single dot, you just simply paste it here. So here will be the authentication part will be done. Now the main thing, like the main tweet extraction thing is done here. So we have another class and another function, say stream tweets. So to do it more generalized, I'm not specifying the file name or hashtag list. So hashtag list, why you need a hashtag list is basically without a hashtag list, if you extract tweet, so you will be getting random number of tweets. Few may seem irrelevant to you. So to customize your data, you can specify a hashtag list. So it will extract only those tweets, like a filtration process. So only those tweets which will contain that hashtag. Along with that, if you don't want to use a hashtag, you can even use say keywords. So the process will be same. The only difference will be like stream.filter track equal to, instead of doing this hashtag list, you need to say like within a third bracket, within inverted comma, you can directly copy paste your keywords separated by commas, and you can like even give like 100 or 10 number of say 10 number of keywords, and it will extract those tweets which will have those keywords, or even those tweets which have just one keyword. So it will extract the Twitter based on that. Now we are printing tweets and there is an error handling process. So if it's okay, then it will simply print the tweet, and if there is some error, so it will print the error message along with the tweet. Now we're doing the data manipulation or say data analyze part. So for that we are doing this, we have a class and doing this clean tweet, and then the main thing is sentiment analysis. So for that, as I already mentioned, we have text block. So we are feeding the clean tweet in here, and it has an already say predefined function like dot polarity. So it will basically assign a number related to each tweet. So if it's greater than 0, it will return 1. So you know your tweet is positive sentiment. Is equal to 0, it will return 0. So that tweet is neutral, neither positive sentiment nor negative sentiment. And if it's return -1, so you know your tweet has negative sentiment. So along with this sentiment, we have some, or we are extracting few other details from that tweets. So first we are converting the tweets into data frame and storing them in a column, say tweets. And with that, we are extracting other detail related to the tweets. So for ID, like from which ID the tweet is posted, the length of the tweet, from which date the tweet was posted, source, say like it was posted from a computer or say app, something like that, number of likes and tweets. So for that we have these functions like dot retweet count, dot favorite count, or dot ID. So one thing I should mention here that this dot ID, dot favorite count, everything along with this package, the complete description of the package is already given along with the how to implement them. So the example with in this description or in this full description of TWP. So you can simply go like twp.org and download the documentation, and if you check that, so there are even other details or other thing you can do related to that data, more than details there. So even if you are new to it, even the coding part will not be a problem to you. So coming to the main part of this code, for example, I am extracting the data based on a hashtag, say hashtag Republic. And for each page, I am say printing 100 number of tweets. The language is English, I have specified, and doing the sentiment analysis with the help of the function that I have already created and storing them in a CSV file, say republic.csv. So you need to mention the hashtag and name of the file here. Now when you will run it, something like this you can see. So here are, along with the serial number, they are the tweets along with their ID, and they have the length, the date, the source from where it was posted, number of likes, retweets, and sentiment are already here. So it might took a long time, even a whole night, but after the end of this, the CSV file, which is the republic.csv, will be created in the same folder where you have the code. So this is finally how the CSV file looks like. In every column, you can see all the details are already stored. So there are a few other options, like even you can extract data from Facebook, but they have these days some limitations. So the easiest option will be extracting data from Twitter, and the basic things that I have shared, with the help of them, you can create your own customized data, completely customized for you or related to your project. And if you go through the documentation of you can even extract few other information and a lot more detail about that. So thank you for bearing with me.
Thank you, Sharnesha, for your beautiful talk. As we are running out of time, we have a very short answer session. So a question was asked by Sombit Bose: what is the difference between data scraping and data crawling? So kind of the speakers will be interested to answer that question.
Yeah, I'll answer that question. That's a very good question, actually. So data scraping and data crawling are sometimes used interchangeably, but there's a very subtle difference. First, I'll talk about the similarity between them. So scraping and crawling can both be used to simulate human users. So you can use a scraper or a crawler to go ahead and log in as a user, or to basically act as a bot. So both of them can be used as that. And the difference is, so for a data crawler, you do not know till what extent a crawling will happen. So a crawler is just let out to the World Wide Web, and it goes to multiple layers to get the information. It is not as focused as a data scraper. In data scraper, you want to get more structured information, or you know what you're expecting, what is the data output you're expecting. But in data crawler, you only have a start seed nodes, and then where the data crawler goes after that clearly depends on how the indexing of the web pages has happened. So in simple terms, scraping is more organized, and crawling is something that depends on the web page itself. Yeah.
Okay. The next question is from J. Mita. He's asking that is scraping and crawling of FB profile data ethical?
So I get where the question is coming from, but when we crawl data, so how usually data is garnered from Facebook is via the Facebook API, right? Which contains data of people and their social accounts and their likes and comments, right? Now all this data, of course, is anonymized. And as an end user, as researchers, we're only consuming the APIs. So we cannot scrap or crawl into Facebook because we will face authentication issues. But when it comes to exposing an API that they have in the form of the Facebook API, that is I think that is garnered by law as well. So yeah, there are licenses around it.
And the tool changer, actually, it is a public data. So there is no to crawl that. This is public in it basically.
Okay, thank you. So this concludes the question answer session. Now we will begin the second part of our session 2, which is primarily on IoT cloud system for monitoring applications by Professor Sharbani Roy. So Professor Sharbani Roy is a professor in the Department of Computer Science and Engineering, Jadavpur University. She received her PhD degree in engineering from Jadavpur University in 2008. She was awarded Fulbright Nehru Senior Research Fellowship in 2013-14 and joined the research program at University of North Carolina, Charlotte, USA. She is a gold medalist both in UG and PG level. Her research interests include cloud computing, wireless sensor networks, IoT, social network analysis, and data science. She co-authored more than 130 research papers in international conference proceedings and journals. She has been involved in technical program committees, organizing committees for many international conferences, and also acted as a reviewer for many international conferences and journals. She is a senior member of IEEE. I would like to invite Dr. Sharmani Roy to begin her talk. Madam, please.
Thank you, Dr. Kingshuk Chatterjee. Thank you for such a nice introduction. Am I audible?
Yeah, you are audible, madam.
Okay. Yeah. So I guess we are running pretty late, 15 minutes late. So I'm not wasting more time here. So I will start my talk by sharing my screen. Is that okay?
Yeah, madam. Thank you.
So my screen is, you can see my screen, right?
Yeah, it's visible.
Okay. So the title of my talk is IoT Cloud-Based System for Monitoring Applications. See, from this title, one thing is very clear that my focus is on monitoring applications. However, what type of monitoring applications, that hint we are not getting from this title. But one thing is clear, is some application where the main objective is monitoring. And this other part of this title, which is indicating the nature of the system, which is majorly based on IoT cloud and using this latest technologies of IoT and cloud. So let me tell you first that what we want to monitor here, or what type of applications actually I am indicating here. Here I would like to indicate applications which are actually occurred due to some events. So let me explain what do I mean by this event. Event is something which actually takes place, right? It could be anything. Now, this term event is not very new to us. We have experienced, or we have know about this concept of event in several streams of our studies, majorly in mathematics and in statistics. In statistics, event is defined as some incident, right? And then it could be categorized as independent event, dependent event, or mutually exclusive event. Independent event is something where an event is not affected by any other event, or an incident which is not affected by any other incident. Whereas the dependent event, something which is affected by other events. And mutually exclusive, it could be dependent, it could be independent, but the major thing is it can't happen at the same time. But one event can hamper another event, or one event can hamper or can affect another event. So I'm taking these definitions from statistics and trying to define the concept of event in monitoring applications, which is the main focus of this talk. So some examples, let me state you some examples, like some random example like party, or say traffic, or after the crop, setting fire to the straw, or some road work going on in our neighborhood. These are some random events, right? But this event can cause another event, or can relate to some another incident. For example, suppose someone is hosting a party, but that party could create some noise pollution. That party can create some noise pollution, and that is not a very happy situation for the neighborhoods, right? Neighborhoods may be not very happy with that event. Similarly, traffic, which is a very important part of our day-to-day life. We cannot avoid traffic, but again, traffic which is creating or causing air pollution. Similarly, setting fire to the straw, that can also create air pollution. Another example, like some road work. Road works are sometimes very important, but when road works are going on, it can create some pothole in the roads. That potholes are not good for us. Potholes can create several problems in daily passengers' life. And that pothole can also cause poor driving, right? So these are the separate random events, but they can impact each other. Moreover, if you think about this factors of events, party creating noise pollution, traffic creating air pollution, setting fire to the straw, creating air pollution, road work or pothole, that is also creating poor driving. It can cause another issues like health problem. They are directly related with our health. They are impacting our health, right? So majorly I'm thinking about these societal issues, these problems of our society, and talking about building some application which can monitor the situation, which can monitor our environment and can help us to solve these issues. So moving forward, some specific monitoring applications that I have selected and which are indicating the dynamics of the city. For example, air pollution, which is a very important dynamics of a city. It talks about so many things about that city, how good that city is for living. Next, noise pollution, then traffic condition in that city, road condition, and along with this, the human mobility and its pattern, if there is any mobility pattern or not, or whether this mobility pattern affecting the human's health or the other factors. So essentially in this talk, I will focus on two major monitoring applications. One is the air pollution and another one is the noise pollution. So let's start with the air pollution. It's a big problem in major cities of India. We will find this type of scenarios in almost every metro city of our country. It's a very common scenario, very polluted, mostly the urban areas, the city area, and mostly it's caused by the traffic. Now, if we think about the noise pollution, that is also a very big problem, unnecessary honking during driving. Then for any gathering, there's unnecessary noise pollution that are causing severe problems in the neighborhoods. Traffic also creates huge noise. And this noise pollutions are actually impacting our health. They can cause high blood pressure, sleeping disorders, heart problems. So they are directly related with the well-being of humans. So that is the reason behind picking these two burning problems of major cities of our country. So now, what is the idea? The idea is we have picked some societal issues like pollution, and we want to monitor this pollution. So, which is under this monitoring application. And then for this, we have to develop a system. What type of system? Majorly IoT cloud-based system. I will discuss why these two components are important in designing this type of system or in addressing this type of issue. So before going to do that, let me explain what are the main components of an IoT system. There could be several components in an IoT system, but I would like to highlight 5 main components. the first one, okay, before that, let me, I hope all of you know that IoT stands for Internet of Things. We all understand what is Internet, and we also have a very good idea about what is thing. The point here need to be considered is that IoT or Internet of Things is a plural. It's not talking about a single object or single thing. It is actually talking about a collection of things, right? A collection of systems, a collection of devices to address some given problem. But there are several solution approaches where one or two devices are used, or some specific application where you don't need multiple devices. So that is actually depends case to case or application requirement wise. Now, just the first component of any IoT system is that thing. So that thing could be any device. Here, to identify that thing over internet, we need this addressing. So sometimes we have to give this internet enabled devices where you have to assign the IP to that thing. Or sometimes it is not required. Sometimes that globally known address is not important to devise that application. And in that scenarios, you can use any ID, any sensor-based ID mechanism, which is performing good in a local environment, and also overall system performs nicely in this setup. So this thing concept is clear, right? I can give you another example of, let me give you one example. Say in this pandemic situation, let us consider a very imaginary situation. Suppose you want to check whether every member of your family are using this sanitizer properly or not. So what you did, you have one bottle of sanitizer and you want your family members to use that sanitizer properly. So you can make this bottle of sanitizer really an IoT bottle. How? You can put some device on that sanitizer bottle to make it a smart one. If somebody used that sanitizer bottle, you will get to know that yes, somebody used it. For that, what you have to do, you have to simply put a sensor there. That sensor will sense whether there is any press on that sanitizer bottle or not, using a pressure sensor, right? There are different IoT devices or boards are available nowadays. Arduino board, Raspberry Pi board. In these boards, you can put some sensors of your choice or as per the requirement of the application, and then you can build your system. In this example, you can put a pressure sensor and can check whether there is any push in that sanitizer bottle or not, and you can take that count. But fine, that pressure sensor can count the number of press in that sanitizer bottle. But how will you get to know that which particular member of your family is using it? To do that, you can add another thing. You can add a communication module in your circuit, and you can tag it with the mobile devices of members. So whenever that person with the mobile devices is close to the sanitizer bottle, it will do this tagging between those two devices and can send you an notification. Now, how will you sure that, let's make this application a little bit more complicated. How will you sure that the person is actually using that thing and rubbing his or her hand? How will you do that? You cannot check these things with the help of your smartphone or with the circuit that you placed in the sanitizer bottle. You cannot do that. Here, something else you can apply. You can give that person a wristband kind of thing where you can put some sensors, say the accelerometer sensor, and tap that sensor with his or her mobile phone. And when that person will be close to that sanitizer bottle, pressing that bottle, that it will count that person and it will check whether there is any change in the accelerometer data that is coming from his or her wristband. And you can make sure that that person is doing the proper sanitization task. right? So in this way, from one thing, one device, you can add multiple devices and can build a system, right? But in this particular system, the devices, that means the wristband, the bottle, they don't need to assign any internet. You can use some separate, some lightweight ID with that. So, so after that, what else you need? You need a local network where you can connect these components, or at least you can connect this different things of the system hierarchically with that point. Why you need that? Suppose you want to monitor the whole system from outside of your home, from some other places. So how will you get all this information? You have to go via the internet. So here you need that gateway. That gateway will be assigned an internet ID, and that will be connected hierarchically with the other components of the system and help you to send the information that you want. Then internet, that is the next important component. If you want to access this application from remote location. Next important thing is the backend services. Now, if you want to do some sort of analysis over this data, if you want to do some inference from this data, some prediction from this data, you need a strong, solid backend services. And mostly this backend services, I mean, most of these IoT devices are not very resourceful. They are lacking resources like processing, memory, storage, etc. So in most of the cases, with the help of current support of cloud computing, you can push all this data to the cloud where you can run your analysis and can get back the knowledge or inference in the front-end device. And the last component is the front-end services, because at the end, as a user, you want to visualize all these insights. And to visualize all these insights, you again need some front-end services. For example, suppose if you want to monitor or if you want to get all these insights in your mobile phone, you need a good mobile application running in your phone. So these are the main components of an IoT system. Next, I will cover some basics of this internet stack and IoT stack. See, this internet stack, IoT stack, all are majorly following this TCP/IP protocol stack, and which is very known to us. In the MAC layer, that is, we have support for both Ethernet and Wi-Fi. Then in the network layer, we have this IPv4, IPv6, transport layer, TCP, UDP. But the interesting part is this application layer. In application layer, for this web-based services or to expose web services, the support of REST API is very effective. So for most of these cloud applications and IoT cloud or smartphone cloud-based applications are using this REST API. So it's not a very major change from standard TCP/IP protocol, just some important application layer protocols are here, like in internet stack, REST API is hugely used. Next is the IoT stack. The standard internet stack is not applicable for IoT. The reason is it's a bit heavyweight. This particular stack is a bit heavyweight because of this network layer protocols of IPv4, IPv6. It's quite heavyweight protocol or heavyweight stack. But as we know, IoT devices are not very resourceful, mainly for the processing, storage, and memory point of view. We have to convert, or for IoT, this stack is actually designed for this constraint part. It's a low complexity counterpart of internet stack. If you look at the changes, the major changes in the data link layer is mainly using 802.15, Zigbee, Bluetooth, this type of Bluetooth, low power, this type of protocols. And then in network layer, there's another major change or adaptation we can say, that is 6LoWPAN, which is IPv6 low power wireless personal area protocol, and it is mainly an encapsulation and header compression mechanism over IPv6. So if you have to assign some IP or addressing for IoT devices in a personal area network, 6LoWPAN addressings are used, 6LoWPAN techniques are used. Then in the transport layer is UDP. Next, for the application layer, again, there are a series of application layer protocols which are designed based on the requirement of the applications. And they are using the security layer and transport layer accordingly. And again, in the application layer, this REST API, which is actually a very good model for any IoT-based application and web-based or cloud-based services. So as I told you, in IoT, application layer protocols are very important because they have some control over the performance of the application that you have designed, and those applications has their own requirements. For example, see this standard protocols that like COAP, constant access protocol, message queue transport, telemetry transport protocol, AMQP, advanced message queue protocol, data distribution system, XMPP, which is XML based. So these are different message passing protocols which are used for different type of application requirements, and they are using the security layer and the appropriate transport layer. If it's an UDP protocol, then DTLS security layer, TCP and TLS transport layer security. It's a datagram transport layer security. So the combination of UDP or TCP with the appropriate security layer and the application layer. So these three things are actually where someone can focus when what type of protocols they want to use for their application. And as I already mentioned that the network layer protocol is mainly 6LoWPAN because of the constant nature of the IoT devices. So basic architecture or the overall architecture of any IoT system is something like this, where you have a thing or things, which is an array of things. It could be multiple things, but everything must have three components. One, it must have some sensor and actuator, sensor or actuator rather. For example, if you want to sense the pressures, you can use pressure sensor. If you want to monitor temperature, you can put a temperature sensor. Whatever thing you want to monitor or sense, you can put that sensor. So that is the important part. Next is the processing. Not very powerful processing, but little bit processing that you have to put in that device. For example, like when you are monitoring or sensing temperature, usually the temperature maintains a particular level. Say, for example, 32 degrees centigrade. There's not much change in that. But if something goes wrong, if something, if some fire is there, then suddenly the temperature will rise. But as long as it is 32 degrees centigrade or 33 degrees centigrade or 31 degrees centigrade, there's no point of storing that data or no point of considering that importance of that data, right? So if it is above the threshold or below the threshold, that is indicating something, some event, right? So then at that point, you can send the data to the next level. So processing part, and to send the data to the next level, you need a communication module. As I mentioned earlier, between the devices, you can use lightweight communication protocol like Zigbee or Bluetooth Low Energy. Or if you want to send it to the next level, to the gateway node or over the internet, then you have to need the Wi-Fi communication model. So now this Arduino board or Raspberry Pi board, they have this functionalities, facilities to attach different type of communication modules like Bluetooth module, Zigbee module, or Wi-Fi module. You can put some processing power there, microcontroller based boards are these mainly. You can put the sensor of your choice. So easily you can build this part with the help of Arduino or Raspberry Pi. And then in that environment, if you want to access that environment from outside, you have to connect that thing with some gateway. So this gateway is one node which is having that IP address, and that address can be accessible from the outside world. This gateway node also having communication, right? But see, there are two communication modules. One communication module to communicate with these things, and another communication module which is to communicate via the internet. And a part of the processing here also to do some little processing. And nowadays this edge computing or fog computing, this type of concepts are coming. So this gateway node is nothing but an edge node. So if this edge node is little bit powerful, you can also assign some computation task in this gateway node that can do its all computation in a real time and can send back you the result quite fastly. So for real-time response, you can consider this gateway node as an edge node. So via this internet, when it reached to the server side, here the server side means an infrastructure which is capable enough to store the data generated by these things, as well as capable enough to perform any computation over the data. So we all can understand it could be a cloud site, cloud server site, or remote server site, where you will easily store all this data. You will be able to execute your analytics over the data. You will generate the insight and then can send back that insight or knowledge to the user. So that is the basic architecture of any IoT system. So next, we all have an IoT device. Every time we are carrying that device. And I know that you all write about this. That is, it's nothing but our smartphone. And the smartphone has this array of sensors. You just name one sensor, you will find that sensor in your smartphone. These modern smartphones are really very rich from the sensor point of view. You will get temperature sensor, pressure sensor, fingerprint sensor, magnetometer sensor, GPS sensor, accelerometer sensor, humidity sensor. There's a lot of sensors, microphone sensor. There are so many sensors. And what we need to do for this monitoring application, we actually need these sensors, because these are the devices which are sensing our environment. So you have this sensor with you. Now I'm highlighting a very interesting fact, which is not related with the sensor and all, but yeah, somehow related. That is about a book. It's a Wisdom of Crowds, written by a very famous New Yorker business columnist, James Surowiecki. And he's talking about a very interesting and simple idea. That is, large groups of people are smarter than an elite few. So what is the meaning of these things? Sometimes we are having problems in our life, in our society, and we assume that the government will solve this problem, ministers are going to solve this problem, and the big people, leaders, they are going to solve this problem, not we. But actually these problems, there are some problems that can be addressed by us, citizens. So this large group of people, the large groups of people, that is the citizens, are smarter than an elite few. I mean, the other part that I have also already mentioned, I'm not going to put more words on that thing. So motivated by this concept, there is this crowdsourcing, crowd sensing, these things are taking place. So crowdsourcing is a very popular, what I can say, a very popular way of involving crowd in different type of projects, different type of programs, and different type of tasks. There's a micro-tasking thing. There's this crowd testing, where crowds are testing softwares, collaborative knowledge, crowdfunding for startups, open innovation, a lot of creative things. Different things are coming up with this word crowdsourcing. And if you heard about this Amazon Mechanical Turk, the Amazon M-Turk, that is a website for crowdsourcing where the different companies are giving the task, and there are different people, they are joining this websites for providing themselves for this task. So that is a very popular crowdsourcing website, Amazon M-Turk. You can have a look on that if you're interested. So under this crowd sensing is another aspect, a very important and interesting aspect. What does it mean, crowd sensing? If you look at this figure, you will see that the crowds are observing something and then they're sensing that or capturing that with the help of their smartphone, and they're reporting these things. For example, here a factory is generating some pollution or air pollution, water pollution, something, and crowds are looking at that, capturing that thing with the help of their smartphone and reporting these things. Here also some traffic congestion, traffic related pollutions that are captured by the citizens and they are reporting this. Here some accident took place, crowd trying to report this incident. Here some garbage, crowd is trying to report this thing. So there are several problems, and crowd is actually taking part in monitoring or in reporting those incidents or events. There are two popular classes of this sensing paradigms, majorly in crowd sensing. One is the participatory sensing. If you look at these examples, all these are participatory sensing. Why it is participatory sensing? Because the participant or the volunteer fully aware about this fact, and he is participating in this task by capturing that situation, by sensing that environment, and by reporting that thing. So in participatory sensing, the participant or the volunteer fully aware that but in the another part or another class of the sensing paradigm, that is opportunistic sensing, it is fully unconscious. And in this type of sensing in this type of sensing application, without the knowledge of participant, you can execute, or the application can execute that sensing task. A very good example of this opportunistic sensing is when we are in some new place, our mobile phone try to capture the Wi-Fi signal, and it is continuously sensing the available Wi-Fi signal and then select the signal with the good signal level. So that is, this kind of sensing task is opportunistic sensing, an example of opportunistic sensing. But participatory sensing is little different, where the volunteer or participants fully aware about the sensing task. Nowadays, there's this concept of crowd reporting in most of the major newspapers like Times of India, Telegraph. The crowd or someone can take some snap of some incident and can report that to the media. So that is called crowd reporting. And this is done with full consciousness. Right, so these are two classes, main classes of this crowd sensing paradigm. So why this participatory sensing is important, or rather interesting? Because with the help of participatory sensing, we can address several issues. What type of issues? The first thing is the availability of sensors. In most of this monitoring application, you need sensors. What are the options? The first option is whatever you want to monitor, you deploy some sensors. That is a static deployment, not very dynamic in nature, fixed, but a very costly affair to deploy some sensors there. But in case of this participatory sensing, as every participant with the smartphone is taking part in this venture, they are having this rich set of embedded sensors. So you don't need to invest anything on the sensor side. Second is the powerful computing and sensing capabilities. All these smartphones, modern smartphones are coming with very powerful computing as well as sensing capabilities. Moreover, they are having this access to the cloud. So computation, sensing, and storage are not a big problem when you are tagging the smartphone IoT devices with the cloud services. Third point is the data. With the help of participatory sensing, you can reduce this problem of data sparsity. That means the lacking of data. You can address this problem because more the participant, more citizens will involve, you will get more data on that particular topic. And the final point is, it is indicating a very cost-effective solution because you can cover a large areas like city without deploying any sensor at all, as well as you can provide services which are very effective for the citizen. So overall, this concept of participatory sensing with the help of smartphone or IoT devices, a very viable solution. And it's a very obvious choice for smart city applications because here you are engaging crowd or group of people or any individual, right? They are taking active part in this type of applications. You're just taking any application, you can involve citizen there. If they're taking part, they will be more aware about the problem. They will try to solve that problem. So these are some benefits which you can also get from that. And when we are thinking about the smart city is actually not a single application. That smart city, a city will be really smart if everything is smart, like traffic, health, road condition, lighting, utility, environment, parking, everything. So smart city is not a single application, it is actually a pool of applications. And in this pool of application, we can utilize this power of IoT, cloud, and data analysis together to build this type of concepts. Now, when we are talking about this IoT devices, we are talking about smartphone as a sensor, IoT device with sensors. We are also thinking about citizens as sensors. So a lot of involvements, but lot number of endpoints. So these will generate huge data, a big data. And if it is possible to analyze this data, then only you will get the actual picture. Then only you will be able to infer, or you will be able to build the knowledge bank. So here, the smartphone and IoT that generates big data. And as I mentioned that these devices are not very resourceful. They have some limitations with their processing, with their storage, with their memory, right? So you need an infrastructure that will provide you the support to this requirement. And for that, cloud is there. So at the bottom layer, there's the sensors, smartphone, IoT, citizens. They are generating this data, and the system will push this data to the cloud environment. And at the cloud end, you will be able to store this data. You will be able to perform analysis over that data. So majorly, we have this idea of different components of IoT cloud system. Now I'm going to put them all together. So what are the main components of this system that I'm talking about? The smartphone, sensors equipped wearable devices, sensors deployed static, these three things, these are making this IoT part. And then this section, this three type of sensors, along with the citizen as a sensor, they're generating huge data. To store that data, to analyze that data, you need cloud. And finally, to make it a workable solution, you need front end and backend codes. So these are the main components of that system. Here I'm showing you a layered architecture by Zheng et al., published in TIST. So the idea that I'm talking about, you will get this in this layered form. Here in this bottom layer, they have this citizens, devices, all in this layer. The endpoints for sensing. So the data coming from this layer is going to this next layer, that is urban sensing and data acquisition layer. With the help of participatory sensing, crowd sensing, mobile sensing, IoT devices, smartphone, sensors, using all this, you are acquiring that data. And next, from that data, you can differentiate that for different purposes. For example, for human mobility, then traffic, air quality monitoring, meteorology data, social media data, energy related data, road networks, point of interest. There are different, you can divide that data into different segments. Now, from this, what you can do different type of analysis. For example, spatiotemporal analysis, stream analysis, trajectory analysis, or any type of graph related analysis over this data. Here you can apply different type of analytics, data mining, machine learning, different visualization techniques. And finally, you will be able to provide some services to the user or to the citizens back, like traffic congestion, some urban planning, some information regarding the pollution, like this. So this is an overall layered architecture of this type of urban computing system. So now I'm going to highlight this participatory sensing based IoT cloud system. So as I told you, I will focus mainly on air pollution and noise pollution thing. So first I'm showing you an IoT device for air pollution monitoring. This device is named as Air Quality Monitoring Device, AQMD. So this is the circuitry of this device. This is a Arduino board. In this Arduino board, we have one communication module. This is a Bluetooth module SC05 used for wireless communication. SC05 that is used for wireless communication. And then there is this gas sensor for air quality measurement, MQ135. This sensor is able to detect or measure NH3, NOx, benzene, smoke, CO2, these pollutants of air. And then there is a particle density sensor. This is a very important thing, very important sensor module of this device. And this sensor is actually measuring PM 2.5 and PM 10. PM 2.5 or PM stands for particle matter in air, particulate matter in air with diameter 2.5 and below, that is PM 2.5, and PM 10 is of particulate matter with the diameter less than 10. These two things are very important to measure air quality index. So just for a reference, I'm saying that the size of the PM 2.5 is very small and very harmful for human health. It's like 100 times lesser than the width of your hair, just to imagine or just to understand. So these components are actually very harmful for human health. So you can build or any IoT device for your monitoring application. Here for air pollution monitoring, we have developed this AQMD device, which is having this sensors DSM-501 and MQ135 to measure different components to indicate the air pollution or to calculate the air quality index. Now, why we have placing one Bluetooth module here? Because this AQMD device will sense the environment, this air pollutants, and it will send those values to the mobile phone. So that's why there is this Bluetooth module, and this Bluetooth module will be tagged with the Bluetooth connection of the smartphone. Now, once we are getting this data in our mobile phone or in our smartphone, we are taking some other sensor values from the smartphone. And what are those sensor values? We are taking this GPS for geolocation of that pollution sample. Then we are taking the system clock for the timestamp and some other context information like the land use or the weather data, etc. Along with these sensors, we can also take the proximity sensor value and the accelerometer sensor value. These sensor values are used for a pre-processing purpose that I will discuss later. With the sensors, there is another sensor, microphone. That microphone sensor is actually used to capture the noise. It measures ambient noise in decibel. So for air pollution monitoring, we don't need microphone essentially, but for noise pollution monitoring, we are using microphone as the main sensor along with the other sensors. So these are the IoT component that I told you about that. After this data, we can also add some sensing context with that. I mean, whether the participant is inside a home or it's what time is specifically. Though we are taking the timestamp, we can easily get that information, whether it's an holiday or not, whether it's a rainy day or not, some meteorology data, some weather information that we are also taking as a sensing context. So that's for air pollution part. As I told you, for noise pollution, we don't need any separate IoT device. We can utilize our smartphone for that purpose because we have this microphone in our smartphone. So here, that microphone is actually the main sensor which is capturing the sound and taking that raw data, putting that raw data into a buffer, taking the root mean square of that data, adding timestamp and location value, that means the system, which is coming from the system clock and the GPS module, and add it to the queue. Where from that queue, the application will pick that entire record and will perform the analysis whenever required. So this is how we can measure noise with the help of microphone sensor. So now the overall system architecture is something like that. There is the bottom layer, which is the data layer. In data layer, what we have the citizen or the participant with sensor nodes. We are not talking about any static sensor and or already deployed sensor. Here we are considering mainly crowd or citizen or participants with smartphone sensor. And then some IoT devices for some special purposes, like for air pollution, the smartphone is not good enough to capture that. So we are using a QMD device as an IoT device. So these things are, the data coming from this layer related with several applications like smart homes, smart buildings, smart parking, smart any smart environment or air pollution, noise pollution monitoring, etc. All this data are pushed to the cloud layer. In the cloud layer, we are performing main computation or the analysis. The data that is collected from this layer, stored here, then we are doing some pre-processing, we are doing the analysis and knowledge extraction. And after that, we are delivering some services to this cloud layer. So IoT part is a bit clear. How we are collecting data with the help of cloud and smartphone, that is also clear. We are pushing the data to the cloud. Now at the cloud end, how we can do that? There are several cloud platforms already available, like Google Cloud Platform, Amazon Web Service, AWS Cloud Platform, Heroku, Azure, and different cloud platforms are already available. more or less the workflow on all these platforms are very similar. So I will describe Google Cloud Platform and AWS and one open source platform. So in Google Cloud Platform, see, this is the sensor layer. From this sensor layer, the data can be collected to any edge device. This edge device could be anything, and a gateway or a mobile phone also. Here you can put some lightweight real-time analytics and machine learning modules to provide the real-time response to the user. And then through this edge device, the data can be pushed to the main section of the cloud platform. So here in Google Cloud Platform, there are three main things. One is the Google Cloud Functions. Cloud Functions is one module where you can define your logic, you can write your functions. Then Cloud Publish, Subscribe. As I told you, what type of messaging protocol you want to use or how you want to publish or subscribe your data, that thing is controlled by the Cloud Publish Subscribe module. And then the Cloud Data Flow. Cloud Data Flow, how the data is coming, how you are updating your device, how you are making the services active at the user end. All these things are connected. And this cloud data flow also in control of or sending the data to the cloud BigTable or BigQuery. For the training purposes, you can use the cloud machine learning module. You can train the system with this module. You can write your own model here, and you can train the model with the data that you have. And then whatever data is coming, you can test that data with this model and can send back the predictive value to the user with the help of this Insight module. Here you will find that Insight module, and that is inferring data from the Cloud Data Lab or Data Studio, different type of visual insights of the knowledge inferring from the data. The similar type of architecture you will get in AWS also. In AWS, they have two separate parts. One is for this IoT part, the thing and the IoT gateway. And then the data that is coming to the cloud side, here you can store the data in Amazon DynamoDB. And on that data, if you want to run your logic, that you can write in AWS Lambda. So AWS Lambda is the module where you can write your logic or you can write your function, which is similar to the cloud functions. Here in Google Cloud Platform, it is cloud function, and in AWS, it is AWS Lambda. And then you can build an endpoint API, and through this API gateway, the user can access the service, user can get the knowledge or can get the insight of this service or application that you have developed in AWS. Beside this Google Cloud Platform and AWS, there are some open source IoT platforms also. I will discuss a little bit about this Things board. It's also following the similar architecture. This part is for the IoT devices or the sensors. This is the IoT devices or sensors, this section. And then there is this gateway part, the IoT gateway part. And this gateway has access to the remote server, that means the cloud. And here they are using MQTT for as a communication between the IoT device and the cloud server. MQTT, HTTP, COAP, any application, I mean, based on the application requirement, you can pick any application layer protocol here. And then you have this message queue and core services that you want to write or you want to run over your data, the analytics. You can create different insights here, and that insights can be provided to the end user. End user can get all this analysis from the cloud platform. So now I think we get this idea of IoT devices, smartphone sensors, how we are using these sensors for sensing our environment, crowd as a sensor, or citizen as a sensors in the bottom layer. From this bottom layer, we are collecting this data, and then we are sending that data to the cloud layer, where we can store this data, we can analyze this data. Now I will focus on the major steps for this application development from the data handling point of view, from the data point of view. So the first step, or the most important step, is the data collection. And as I told you, in the bottom layer, we have the smartphone as a sensor, we have IoT as a sensor, and citizen as sensor. They are actually providing this data. Through them, we are collecting this data. We can rigorously collect this data through participatory sensing. We can involve citizens to take part in this type of process. And finally, we can eliminate this data sparsity problem of pollution monitoring. After first step, we have data, but that is a raw data. We need to do some pre-processing on this data. So mainly two things here I've focused. One is the context-aware data cleaning, and next is the calibration. Context-aware data cleaning means I know some situations, some contexts are there where the data, if the data is associated with that context, it is not useful. If I have this knowledge, then I have to exclude that data. I have to exclude that part from the data. So this is called context-aware data cleaning. And second is the calibration. Calibration means we are using smartphone sensor or sensors that we have used in our IoT devices. These are not very costly sensors. So sometimes the quality of the data is not very good. Sometimes they are not at par. So if we have some standard devices, then we can devise something for calibration. We can impose some calibration over the data, and we will process that to reach the quality, to improve the quality of the data. So context-aware data cleaning and calibration, that is these two things are important. And finally, the data analysis. Here in data analysis, we can apply different type of predictive models. We can apply different type of learning methodologies to infer the knowledge. Here, for this particular application, air pollution and noise pollution monitoring, we have focused on spatio-temporal analysis because it has the spatial effect in its data, it has the temporal effect in its data. So we are trying to do this temporal analysis, we are trying to do spatial analysis, and then the spatio-temporal analysis of the data. Sometimes we have to do this data fusion. When data is coming from different sources, we can apply some fusion techniques to improve the quality of that data. So that is all about the third point. The final point is the visualization, and this is a very important point. The reason is the user is going to visualize that thing. So what service you are going to provide to the user is actually controlled by this visualization thing. If the visualization is good, the user will be satisfied by that service. For example, as a citizen, suppose from this application, my expectation is to understand my daily exposure to air pollution. So I need a very particular visualization for this service, because here my objective is to know my daily exposure to the air pollution or say noise pollution. So I need appropriate visualization for that, visualization services for that. Another example, suppose I want to go some particular place. Before going to that place, I would like to see the pollution level in that place. Again, I need some visualization for that. So this step is important for providing service, or it is indicating the quality of service that we are giving. Now, I'm focusing on this air pollution monitoring problem. So why I'm thinking so much about the air pollution monitoring problem? There is this pollution control board. a central pollution control board, and then state-wise there is a pollution control board. They have pollution monitoring stations. Yes, this is the standard mechanism or traditional mechanism of doing air pollution monitoring in India as well as in other countries also. There's this board and they have this monitoring stations. Let me tell you the positive side of this approach first. These pollution monitoring stations are very well equipped. They have a very costly devices to sense their environment. Accuracy is really very good. But in a city like Kolkata, there are hardly 7 to 10 such type of pollution monitoring stations. One station is in Victoria Memorial, near Victoria Memorial. Now you just assume, I'm staying close to the Ruby crossing. So is it possible to know the pollution, air pollution near the Ruby crossing with the pollution monitoring station at Victoria Memorial or some other stations? It's not possible. It's not possible to know the pollution, air pollution level at your place. It's not possible because you don't have a monitoring station there. So that is the problem with this traditional approach, data sparsity. You don't have data. You have data in some specific locations. And another point is they're very costly. You cannot deploy these monitoring stations in every road junction or in every corner of the city. It is not possible. It is not a viable solution. So participatory sensing based approach could be a viable solution in this situation. Same for the noise pollution monitoring. If you look at this, if you look at this figure, in this figure, this green points are the monitoring stations in India. And this part is the Kolkata part. And here you will find very few, hardly from 7 to 10 monitoring stations. Most of them, few of them are not working always. So same for the noise pollution monitoring station. And in this country, there are very few. See in this map, you will get seven noise pollution monitoring stations. So it's not at all possible to capture the noise pollution level at every point or at your neighborhood with the help of this traditional approach. So the solution could be this participatory sensing based pollution monitoring, where we citizen can take part in collecting data and in providing input to this particular application. Next, I'm showing a Greenpeace India report. This is of 2018 report, where PM10 air quality by state and for districts with data is showing. Here, the red line is actually indicating where this value exceeds twice Indian national standard. And this yellow one is showing where the value exceeds Indian national standard, and the green one where it exceeds WHO guideline. Now, the West Bengal state is somewhere here, this point. So this is the West Bengal state. So if you look at this data, you will see there's some part where it exceeds twice Indian national standard, and major part where it exceeds Indian national standard, and the rest part, which is very nominal, where it exceeds WHO guideline. So the real scenario of air pollution is really very bad, according to this report again. And this is another report where it is showing the air quality data coverage by state. And the green one is real-time data, the yellow one is manual data, and the red one where we don't have any data, no data at all. So here the West Bengal is in this, this is West Bengal. So no data in some area, in major area, it's a manual data. We don't have any real-time data. So if we involve the participatory sensing, we may get some real-time data. But in Delhi, see, there is real-time data available because now Delhi is taking this pollution problem very seriously. They have so many monitoring stations in the city. And it's the capital, so they are taking this very seriously. But it's not the case with our state and the most of the states of India. So, going back to the data collection part. So what we are taking some smartphone sensor data, majorly GPS, accelerometer, proximity, some air pollution data, air quality index, PM 2.5, PM 10, CO, SO, NO, etc. Noise pollution data, mainly noise value that we are taking from the microphone in dB, the honking rate when we are monitoring the honking rate in car, and the noise pollution in traffic junctions, etc. Meteorological data, here we are considering wind speed, temperature, rainfall, and different type of other meteorological information if available. In contextual data, we are considering traffic condition, crowd flow, and in land use data, we are taking whether it's an urban area or semi-urban area, whether it's a residential area or commercial area, how far it is from the main road, that is distance from road. So these are some factors that we are considering while we are collecting data. So we have this application called JUSense. Under JUSense, JUSense stands for Judicious Urban Sensing Task, and under this there is this AirSense and NoiseSense applications. So in AirSense, we are taking all this sensor data, that longitude, latitude, accelerometer value, air context, whether it's outdoor or indoors, region category, street or road, AQI value, PM 1.0, PM 2.5 value, and other weather-related information, etc. Similarly, for NoiseSense also we have this application with the appropriate geolocation value, accelerometer value, only the noise value in dB, and the other context information. So for site selection, we have considered a neighborhood of Jadavpur area for urban region, and for semi-urban, we have picked a region of Baruipur. So for urban area, these are the information. It's extended between this given longitude and latitude. And the size of this area is approximately 10 square kilometer, whereas in Baruipur, the size of the area is approximately 10 square kilometer. And we designed this data collection part in two ways. One is the participatory sensing data, and another is the ground truth data. In ground truth data, we are taking some standard devices like AirVida and other pollution monitoring devices. We are using the data collected through the standard devices as a ground truth. And then in participatory sensing data, we again divided into two categories. One is the indoor environment and another one is the outdoor environment. And with the help of the participants, or mainly volunteers, we have collected this data. Then, as I told you, this data collected through this participatory sensing, that's the raw data, and we have to perform some pre-processing over the data to further analyze that. So here, we picked actually three problems. One, which is related with the context. Let me give you one example for this context. For example, suppose I'm doing this noise pollution monitoring with the help of my smartphone. And during the data collection, or when I'm using that application, suppose I'm getting some call and I've taken that call. So when the call is in progress, at that time, microphone is actually used by that call. So as well as it is used by that application. So whatever data I'm getting is actually of no use. So if a call is in progress, we have to exclude that data from the actual data set. Similarly, for this monitoring applications, it's better if you hold the phone in your hand in a specific position. If you put that phone in your bag or if you put that phone in your pocket, then the microphone is actually getting some obstacle in capturing the noise. And that data is again of no use. So context-aware data cleaning is all about this. If you understand the context, based on that, you have to clean that data. You have to exclude that part of the data. Next problem is map matching. We are using this GPS sensor for getting this location information, but GPS sensor is giving us this long lag value. And when we want to see that in a map or in when we want to visualize that thing, you have to put that long lag value in an appropriate location, because you have some map in your phone and that GPS location will be placed on that map. And sometimes there is a mismatch in these two values. The GPS location, suppose you are in a road junction, but it is showing away from the road when you are putting that in the map. And that is because of this mismatching. So here we have to do this map matching. So the second part is the map matching. And the third part is most of the smartphones are using these sensors which are not very accurate, which are not highly accurate, I must say, but they're fairly accurate, not highly accurate. So sometimes it depends upon what type of smartphone you are using. If you're using very costly smartphone, probably the sensor are of good quality, but if it is not a very costly smartphone or if it's not a very branded smartphone, then the sensors probably are not that good. So there are situations where you may face this type of problems where the data quality is not good because of this low cost sensors or low accurate, not very accurate sensors. So these problems can be handled with the help of calibration. So after doing this context-aware data cleaning, map matching and calibration, we will get this pre-processed data. Pre-processed data and so these are the things that I have mentioned. If your phone is in a pocket or in bag, it will be deviated from the ground truth and not usable, so you have to exclude that. And for best quality noise pollution data, that can be recorded when the phone is held in the hand, but it is not always the case. So you have to understand this context first and then you have to exclude that. Similarly, the noise levels recorded when an active phone call is in progress are not usable. Again, you have to identify this context and exclude that. And GPS data, this raw GPS data, sometimes suffer from very low accuracy near tall buildings or bridges and trees covered areas. So in that cases also, you have to perform this map matching. So the first concept of this context-aware data cleaning, first you have to discover the context, whether call is in progress or phone is in hand or phone is in back pocket. And then you have to exclude these two things and consider phone is in hand part. The second problem that I told you about the calibration, as we have the standard devices, with the help of the standard devices, we can get the ideal response that we can consider for that sensor value. So in ideal situation, the sensor reading and the ideal response both will be similar. So there is no problem. They both agree with each other, so you can consider this data. But in reality, this suffers from very poor measurement accuracy, and there is some difference. But if you able to fit some linear model or some model here, you can also perform the calibration. I mean, some plus minus threshold you can apply if it's a simple linear, if it is following simple linear model. In most of the cases, they are following simple linear model. So with the help of regression, you can figure out whatever the threshold value is, and you can perform that threshold plus minus threshold thing with the sensor to get the actual value. So this is the solution. Here the calibration is nothing but finding a relationship. So as I told you, if you look at this figure, it's following a very linear trend. So you can easily figure out the threshold value required for the calibration here. Next is the analysis part. Now, after this pre-processing, you have this data where you can apply your analysis. As I told you, here in this type of application, air pollution or the noise pollution applications, you can apply spatial interpolation technique, and you can do the spatial analysis, temporal analysis, or spatio-temporal analysis together also. For spatial interpolation techniques, the popular techniques are mainly non-geostatistical, geostatistical, and the combination of these two. In non-geostatistical, there is this natural neighbors based technique, inverse distance weighting technique. And in geostatistical, a very popular technique here is the Kriging technique, which was devised by the Danny Craig. And there are different variants of Kriging techniques are also available to address this spatial interpolation related problems. Some of them are like simple Kriging, ordinary Kriging, universal Kriging. And there's another approach where it combines this neo-geostatistical and geostatistical approach together, which is called as the regression Kriging. And nowadays, this machine learning techniques are also used for spatial interpolation, like support vector machine, random forest neural network. So different type of models or techniques you can apply over your data to infer knowledge from this. I will give you a very simple example of this non-geostatistical technique like inverse distance weighting. Suppose in a given area, there is some points, right? So this blue line is indicating the search radius, and between inside this blue line there are 6 points, where 5 points are known and 1 point is unknown, and outside this search radius there are 3 more points. But these 3 points are of no use for predict the value of this unknown point. Here to predict the value of this unknown point, this 5 points inside the radius will be considered. And here the idea is inverse distance weighting. That means the point which is far away from the unknown point will get less weightage. The point which is closer to that point will get more weightage. So that is the very simple concept. So here you can predict the value of a given location, say XY. You can predict the value of a given location XY, and for that what you are taking a weight factor which is indicated by the lambda, and another is the WI, or the value of that location. So here suppose there are n number of known points, so 1 to n, so summation of lambda I WI equals to 1 to n. That will help you to get this predicted value at location XY. And it is based on inverse distance weighting approach. So here it is the lambda, or the weight, is actually calculated inversely. I mean the weight is assigned as an inverse proportion to here. So 1 by di, and here the summation of k equals to 1 to n, 1 by dk to the power p. Here p is the power parameter. The role of power parameter is to influence the weighting of this factor on W. So how it is putting the weight in calculating the predicted value at unknown location. So that is the concept of inverse distance weighting. So next, as I told you, in geostatistical approach, you can consider Kriging as a solution approach. Kriging is giving a very elegant results sometimes. I mean, depending upon the data, you can pick what particular variance of the Kriging is suitable, and if you apply, you will get a very good result for spatial interpolation. Kriging mainly based on this concept of semivariance. So here it is measuring the spatial correlation between the points. And semivariance, first it calculates the semivariance and used it to predict the value of the unknown points. Here, if you assume that there are 2 points, say xi, and another point which is say h distance away from the xi, which is denoted here by xi plus h. So you are calculating the variance here first, that is xi minus xi plus 1, or xi, in this case xi plus h whole square, summation 1 I equals to 1 to number of observation, that is n of h, divided by nh. So that is what you will get from this. You will get the variance. You are getting variance from this part of the equation, right? And semi-variance means half of that variance. So you are getting semi-variance of that. So once you have the semi-variance, you can plot that as a function of distance or log. For example, here you can plot two model, or you can fit two model here, say the spherical model in this data set, and here in the same data set exponential model. Now by calculating the error, you can figure out which particular model is best suited with the data. So you can pick the spherical model or the exponential model by analyzing the error. So the estimated value of an attribute at any point of interest, say x0, that is nothing but the E of, that is nothing but the E of this part, which is z of x0 minus mu. Here mu is the known stationary mean, and that you are getting from this expression. So here this lambda I, as I told you, it's a Kriging weight which is used to indicate the importance of that value. Here the value at position xi, and mu x0 is actually the mean of samples within that search window. So by calculating this, you will get the estimated value of an attribute at interest point x0. Now in this way, you can figure out the estimated value of any given attribute for unknown points. As I told you, there are different variants of Kriging, most popularly ordinary Kriging, simple Kriging, and universal Kriging. There is slight difference between this Kriging techniques. In ordinary Kriging, here they assume that the constant unknown mean only over the search neighborhood of x0. That means here in this region, they are within the search radius, they are considering that unknown but constant mean value. So that is the basic assumption behind ordinary Kriging. And for simple Kriging, here the assumption is stationarity of the first moment over the entire domain. The stationarity of the first moment, that is the. So that is the assumption behind simple Kriging. And for universal Kriging, it is an extension of ordinary Kriging. Local trend within the search window, universal Kriging is the best choice. So next, going to towards this machine learning methods. In the machine learning methods, you have different data sets like point of interest, meteorological data, traffic data, and different features you can extract out of that. Meteorological features like temperature, humidity, pressure, wind speed, weather, whether it's a cloudy, foggy, rainy, sunny, or snowy, whatever the features are important for pollution that you can consider here. Traffic and road related features are also you can consider. Other features like land use or category of point of interest, etc. So feature extraction plays a very important role in machine learning based methods. So once you have this data set, then you segregated that data set into different modules like AQI or PUI data, road network data, meteorological data. Then you are extracting feature from all these different types of data sets. Then you have the set of features. You can learn your model, and then you can infer from that what you want to predict. So this is the overall structure of any machine learning based models. Next, I'm going to the popular software for spatial analysis. There are several softwares are available. ArcGIS is a very popular one, but it's not free of charge. Some free softwares are also available, like Saga. Different things are different softwares which are free of charge are available. They are running in different, in most of the operating systems code. They have a very interesting features. Among them, QGIS is really very good. It is very easy to use. It has the ability to expand functionality with the Python plugins. You processing functions are already included here. So it's very easy to handle. It's very easy to club with your own methods and own models. So now I will show you some of the visualization. As I told you that it's a very important step. And here, from this step, you are actually providing service back to the citizen or the crowd. So this is the result where we are showing that individuals' exposure to air pollution. There's a data collected by volunteer. I guess it was a bike ride. He took this route, and the pollution exposure are actually mapped here. Then pollution map for both indoor and outdoor environment. This is the indoor environment. There's a 4th floor of our university in our building actually. So in different rooms or in the corridor, the AQI exposure of the volunteer. And see, in here you will find that inside this hall and in this room, the AQI exposure is really very good. It's green, and it is within the 0 to 50 range. And the reason is that these 2 rooms are actually AC room, and the other rooms are not AC. And these 2 points, they are really very poor pollution AQI values, because there are 2 AC connections are here. So that could be a reason behind this. Okay, let me tell you one thing. This AQI, Air Quality Index, this actually vary from country to country, but every country has their range like this. And here we have followed the standard of our country. And here 0 to 50 or 50 to 100, that is moderate or good range. And this map is the AQ map for outdoor environment. Next is the air pollution map after a spatial interpolation. This is as I highlighted the urban study area, which is near the Jadavpur University. In this area, so the thing is, suppose we assume that this is the initial graph, right? And these are some points where the participants have collected this data. And there, this particular graph is for one participant, but for multiple participants, we may get different such type of points. Now, when you have this graph, if you put a grid over that, you will not get values in each and every grid cell, right? And here, to predict the value in the grid cell, you can apply this spatial interpolation technique. So after that spatial interpolation technique, we will be able to predict the value of the grids where you don't have any participant data. So after that step, you may generate this type of air pollution map with the contour lines and with different color codes for EQI values, where 160 is for blue and 200 for red. So it's a very polluted area, a less polluted area. But all are above the good and moderate EQI value level decided by this country. This is one study that we did in last year during Diwali. And I hope you remember that during the Diwali days, the Kolkata city was almost on the top of the most polluted city list of India. So this is the data during 7 p.m. to 7:30 p.m. And this is during, in the same road network, it is during 8 p.m. to 8:30 p.m. You can easily see the changes. I mean, it was very polluted at that time. Next, another study we performed after Bulbul, that cyclonic storm, in the month of November in 2019, that hit quite well in Kolkata and Bangladesh. It was a very, big storm and very flash floods across that regions. So this is the path of cyclone Bulbul. And after that, when we analyze that data, we get this type of result, where this section is the pre-Bulbul scenario. This section is the pre-Bulbul scenario. This is the during Bulbul, and this one was the post-Bulbul. During Bulbul means, the next 2-3 days after that storm day. So, previous days of pre-Bulbul scenario, it was quite high, very polluted of PM10 and PM2.5 level in that study area. But during Bulbul, it was really very low. And after Bulbul or the post-Bulbul, then there will be, you can find the very distant peaks in the PM10 and PM2.5. And we also thought about that doing the same kind of study during, after this Amphan. But, Amphan was in May, was in the month of May, and during that time lockdown was already there, so already the pollution levels are quite under control, so we didn't get this type of nature for Amphan, but we get this distinct difference for Bulbul study. Now, some individual exposure to noise pollution. This personal exposure to noise during a city bus trip in following this route. And then there is this overall city's noise pollution map. These are the discrete values, but there are some points where you don't have these values. By doing the spatial interpolation techniques, we can also generate that continuous pollution map. These are the some pollution, noise pollution exposure, individual noise pollution exposure with time on the road while traveling. And this is in the Jadavpur University Salt Lake campus. As I told you, these are some discrete values. In all points, you don't have the data points, but after interpolation technique, you can get that value like this. So this is the noise pollution map generated after that spatial interpolation technique. Indoor and outdoor air and noise pollution technique. Here, indoor, DST feast lab, that is the indoor scenario, and outside of the DST feast lab. That is a very small study where you can get to know that the impact of pollution at indoor and outdoor at different time of that day. And this particular application or the service, as a visualization to the crowd or the citizen you can provide, where as I told you, JUSense is the name of the application, stands for Judicious Urban Sensing Task, or JU also stands for Jadavpur University. And here you can pick some service like air pollution map or noise pollution map, air pollution map or noise pollution map. And then you can select some area. Here we have selected the Jadavpur Thana area, same here. Then you can pick some session like morning session, afternoon session, evening session, night session, because there's the impact of pollution. There's a change in this impact of pollution in different sessions. Sometimes in morning session, there is a very busy traffic for office or school, not in present scenario, but in normal scenario. So the pollution effect will be different in morning session and in the afternoon session. So in this way, you can generate this pollution map as a service to the user. Now I'm almost end of this talk. Next, I will highlight some of the opportunities and challenges of this type of approach. So mostly I have highlighted the main thing about this type of applications where we can involve crowd or citizens. The main idea is point around participatory sensing with the help of IoT cloud system or IoT cloud technology. We can design an end-to-end system for this type of monitoring applications, which are addressing several society applications or issues. Now, what are the positive sides or opportunities here? The positive thing is this solution, this type of solutions are very low-cost solutions because you don't need to bother about any other sensors. You don't need to deploy them. You don't need to think about the security of the sensors. Everybody has smartphone. They are using the smartphone, and this is very common nowadays. They are coming with a very rich set of sensors. Next, human involvement. Large number of individuals are involved here. Crowd or citizens can take part. They can extract and share this information. And if they take part in this type of ventures, their awareness will also improve. So it's good or win-win situation for citizens. Mobility. Human mobility, that can be also exploited here to improve the sensing coverage or the data transmission, because not in the present scenario, but again in the normal scenario, when a participant is moving from one place to another place or through its traveling profile, we can cover several points, or we can address this issue of data sparsity. So overall, this solution is very scalable, very extensible, flexible, and very easy to maintain, because here the first thing is you don't need to bother about the maintenance of the sensor. Everyone is taking very good care of his or her own smartphone. They are changing their smartphone in every 2 years. So every time you will get a very good sensors. So it's a good thing, good condition. You will always get the sensors in a very good condition. So these are the main plus points. But there are several challenges also. The first thing is, why will someone want to share their data? It may reveal their private and sensitive information. Why will they want to share their current location? So privacy concern, a very challenging thing. Next, why somebody will participate? What is his or her benefit? They are using their own resources. They are using their battery, their computation power. They have this potential privacy threat. Then why? Is there any incentive? So another very interesting and challenging thing is how to motivate participants so that they can take part in this type of actions and this type of ventures. Is there any incentive? Only awareness probably is not a very good incentive, right? So they need something more. So Amazon, I mentioned about this Amazon MTurk in this crowdsourcing website. The company, those who are offering this task are also offering some monetary benefit to the to the participants. So this type of incentives are really very encouraging. But again, some mechanism, there's a huge scope of developing some mechanism which is good for both the service provider and service executor. Some intelligent allocation of the task among the crowd. I mean, how they will be benefited, whether they are doing any cheating with the data or not. So there are several challenges also involved here. The third point is sensing quality. As I told you, these sensors are good, but not always. So sometimes we may need to compromise with the quality of the sensor. The sensing data is not that good. And moreover, there's a difficulty to guarantee the coverage as well as latency and confidence of that sensing data. And the fourth one is the context. So here we are involving human, and human is also providing some context, whether the the residual battery energy or the travel pattern of that user, or the position of the smartphone, whether he hold that smartphone in hand, whether he properly following all the steps of collecting that data or not. So, you cannot guarantee these things. So context detection, context based cleaning, context-based treatment of the data. These are actually challenge. It's not always possible to identify the context properly. If it is possible to do this automatically, then it could be a very good solution. So there are several challenges. There are several scope of doing research in this particular field. And moreover, this type of solution are, very interesting to execute, as they has a direct link with some societal issues or societal problem. So that's all from my side. There are some papers that I have highlighted here. This co-authored by my team, my students, and myself. And finally, I'd like to acknowledge the work of my students. I'd like to thank my student Asif Iqbal Midda. He is doing really good work. He's working really very hard in this particular research area. I also like to thank Joy. He is also my PhD student. He is also working related to this area. Rituparna, she is also working in this area. So I'd like to thank all of them. Also like to thank volunteers from Jadavpur University for their participation. Time to time they have participated and they have helped in building different modules of this framework. And finally, I'd like to thank West Bengal DST for a project they have funded, and this part is actually part of that project. Thank you. So,
Thank you, Professor Shobhani Roy, for such an interesting and informative talk. We will have a very short question answer session. So the first question is from Shohini Dashgupta, and she is asking that how will we understand about the presence of context from the data?
Yeah, so actually it is, as I told you, that understanding the context from the data is not an easy task. Sometimes with the help of other sensors of a smartphone, like say the proximity sensor, with the help of proximity sensor, you can identify whether the phone is in your hand or it is in your bag or it is in your pocket, right? With the help of accelerometer sensor also you can identify that, or the combination of proximity light sensor and the accelerometer sensor. So by utilizing different sensors, you can identify the context, whether it's the right context or not so right for that data.
The next question is from Jay Mitra. He is asking that between Raspberry Pi and Arduino Uno, which is the better choice to read simple sensor data, which includes some computations as well?
Both of them are good, but Raspberry Pi, I mean, you will get several modules of the Raspberry Pi, which are actually a little bit more powerful for performing different type of computations. So yeah, if I have to pick any one of these two, then probably the Raspberry Pi.
Okay, the next question is from Paramita Thakur, and she's asking, what are the popular methods involved in context-aware data cleaning and calibration?
Yeah, the calibration. So the first thing is the context-aware technique. So there is no such standard techniques. You have to understand the data first, and then you have to figure out which particular method could help you to perform that task. Like for the context data cleaning, once you know that with the help of the other sensors, if you be able to identify the right context and the wrong context, then it is a very easy task to exclude the data which is associated with the wrong context, right? And you just pick the data which is related with the right context. And for the calibration thing, you need some standard data which is probably coming from some standard devices where you can, which you can consider as a ground truth. So once you have that data, you just take the relationship with the data that you have, which is coming from not so standard devices with the standard devices. Once you explore that relationship, you can easily figure out the mathematical formation of that, and you can just fit the curve, and you will get what function is appropriate to establish that relationship and use that function.
Okay, the second last question, how to handle the positional variation of the data, because somehow it depends on the position of the smartphone as well. So this is again a question from Paramita Thakur.
I'm not getting the question once again.
How to handle the positional variation of the data? Because the information is coming from the smartphone itself. So how to correct it or handle it actually? So that is what she's asking.
Okay. See, so it's a research challenge. To improve the quality of the data. You cannot force a user to hold that phone every time in his or her hand. Right, but the requirement of this application or the situation is when he or she is holding the phone in his or her hand, then you are getting the right data. Right. So first thing is you have to identify that section of the data, and then you are taking that part only. But whatever data, if it is not holding properly, but still you have some data, the next task is it possible to improve the quality of the data somehow? Is there any technique to improve the quality of the data? That is a research issue. That is a research challenge. There is no standard solution for that. Right? We are presently working on that problem also. So the task is how you can improve the quality of the data, though the data is not coming from the right situation.
Okay, madam. The last question is the JUSense app available in Google Play or JU website?
Not yet. It's not available right now, but my students are really working hard. I hope and dream that someday it will be available, and I wish all of you will use it.
We certainly will. So thank you, madam, once again for such an interesting and informative talk. This concludes today's session. We will meet again tomorrow at 11 a.m. with our session on quantum computing. Regarding queries on feedback form, it will be provided as a link form in the chat box as well as in the description box of the YouTube live channel. Also, a quiz on session 2 and 3 will be provided. We look forward to having you here again at 11 a.m. tomorrow. Good evening. Thank you for coming today.
Thank you, Dr. Krishnendu Chatterjee.
Thank you.